automatically detect those clusters and deploy add-ons and applications directly. So no registration needed with those clusters. And the bread and butter, if you ask me, and that's something I use on a daily basis, Sveltos supports an advanced framework and dynamic templating all in one tool. So you don't have to install something additional. Out of the box, you will have those functionalities. By event framework, what we really mean, Sveltos has the capability to define an event. Sveltos is going to listen to that event and then trigger an action in exchange. For example, if you monitor for service of type load balancer in XYZ clusters, Sveltos will know about it and then trigger, for example, a network policy in exchange that's going to block traffic coming from the outside. And dynamic template, what that means in a Sveltos context, effectively you can templatize your manifest files using Lua and Shell programming language. Sveltos is going to use the information located in the management cluster or brought somewhere from the outside and dynamically pre-insert those templates. So one template to deploy different things across a fleet of clusters, so makes our life easy. And of course, we're in 2026 presenting Svelto is suitable for AI and ML workloads. In the community, it's used for A/B testing, progressive rollouts, operator management, like media drivers. Svelto's pipelining for progressive rollouts as well. Now let's go into more details. Gianluca.
Thank you. Yep, I'm going to cover Svelto's architecture. Can you go to the next slide, please? Thank you. So Sveltos is a set of Kubernetes controllers that sit on the management cluster. And from that cluster, they can deploy application and add-ons on a fleet of Kubernetes clusters. As Eleni said, it has built-in support for cluster API. So if cluster API is running in the management cluster, as soon as you create a cluster with cluster API programmatically, Sveltos detects the clusters and can start deploying application and add-ons on that cluster. But any other clusters can be easily registered with Sveltos. Registering a cluster with Sveltos consists in creating 2 resources per cluster, a Sveltos cluster instance, and the secrets containing the kube config to access the managed cluster. Once you have those cluster resources in the management cluster, you can add labels to those clusters here, and then you can create a cluster profile. A cluster profile is a custom resource definition introduced by Sveltos, where you use a cluster selector, which is nothing but a Kubernetes label selector to select your clusters, and then you specify what you want to deploy. And it can be an M chart, it can be JSON, YAML, customize, whatever you want to deploy, and it will deploy. It has a drift detection mechanism, because if you are in this state, your desired state is what is defined in the management cluster. And so if someone manually changed something on one of the managed clusters, Sveltos detects it and overrides it. So it brings back the desired state and the current state in sync with the desired state. Yeah, thank you. Where does it fit? I personally use it along with Flux. So GitOps repo, where the configuration is defined, Flux syncs to the management cluster, and then Sveltos distributes to the managed clusters. Other companies using Sveltos, they use it in combination with Argo CD. But essentially what we see is that there is always a GitOps approach to the management cluster, and then Sveltos to distribute to the various managed clusters. That is the most common use case. This is just one example of all the tools that I mentioned so far. We have a management cluster. Cluster API is in the management cluster, Sveltos in the management cluster, and either Argo CD or Flux CD are there. So what we want to do in this case with Sveltos is to create a new cluster using cluster API every time a new user logs in or a new user is added. So think if in our Git repo we have a config map defined, and this config map contains the cluster API configuration which is needed to create a cluster with cluster API, and is expressed as a template. So this config map is synced to the management cluster with other, again, either Argo or Flux. And then we have another config map where we have the list of our users. So think of this config map where in the data section you have the user is the key. So all the users, there is one key per user. And then the value is the arguments that we need to use to instantiate the cluster API template to create a cluster for that user. So now a new user is added. This config map is updated. Sveltos sees that the config map has a new entry. It takes the value associated to that user. It takes the cluster API configuration, which sits in a different config map. It instantiates this config map using pretty much the user value. And it creates those resources in the management cluster. Cluster API is there. It sees that those resources are created and reacts by creating, in this case, a cluster on Azure. As soon as the cluster API is created, because we are labeling the cluster requiring Sveltos to deploy Cilium, Sveltos detects that this cluster has been created. It has the labels that require Ciliums to be deployed, and it acts by deploying Cilium. And so new user is added, and automatically a cluster with all the applications that we want is created for the user, and then we can just get the kubeconfig and give the cluster to the user. User is removed. The flow is the same. Sveltos detects that the user is removed. It goes and undeploy all the cluster API resources that were created for that user, causing cluster API to delete the cluster. Sveltos has few custom resource definition. So far, we talked about the cluster profile. The profile is one other resource. The only difference between cluster profile and profile is that the cluster profile is a cluster scope CRD, while the profile is namespace scoped. So if you are a platform admin and you want to deploy, for instance, in all your production cluster, you want to deploy Cilium, you use a cluster profile. It's going to match, once you define a cluster selector, Sveltos is going to find all the clusters that match that cluster selector, irrespective of which namespaces they are. But if you are a tenant admin and you want pretty much to deploy an application on a subset of the cluster, only the one that you own, you can use a profile. The profile namespace scoped. So when you define a profile with a cluster selector, Sveltos is only going to find cluster that match that cluster selector and that sits in the same namespace of the profile. Yeah, I don't know if the font is good enough here, but this is an example of a cluster profile. There is a cluster selector, which is a regular Kubernetes label selector, and we are selecting all clusters with label environment staging. And then we are listing all the things that we want Sveltos to deploy on those clusters. And so in this case, it's the kernel chart version 333, and with certain values. We want the admission controller replicas to be 1. And then there is another section, the policy ref section, where we are telling Sveltos, by the way, get the content which sits in a repo that Flux is syncing and deploy that one. So in this case, we have Flux, which is watching for your Git repo. We have a Flux Git repository. So it's watching, Flux is watching for this, any change in this Git repo. When any change happens, it updates the Git repository artifact version. Sveltos detects that the artifact version has changed. It takes the content from Flux and deploys to all the clusters with label environment staging. So this is a combination of Sveltos plus Flux. And today demo, the demo that we have, it's I'm just concentrate on the part on the left. I mean, from Sveltos on. The other part we are all familiar with. So what we're going to ask Sveltos is to deploy Cloud Native EPG in one specific cluster. So we have a fleet of managed clusters, and in one of those clusters we tell Sveltos deploy Cloud Native PG. And then we also tell Sveltos, anytime you see a managed cluster with a label Postgres required, you have to do two things. Go to the cluster where Cloud Native PG is present and create a cluster in that a Cloud Native PG cluster. That will cause Cloud Native PG to create a database. as soon as the database, Cloud Native PG is done creating the database, which is exposed to a load balancer service, Sveltos takes the load balancer service IP port. It takes the credentials, which are stored like in a config, in a secret or config map, I forgot, in the cluster where Cloud Native PG settings, and then in response deploy a job in the cluster, in the other managed cluster. And this job now has all the information to access the database because it has the load balancer IP port and it has the credentials to access the database and creates a table in the database. So in this case, we are using like an event framework to instruct Sveltos to do all those things for us. A cluster is labeled with Postgres required, and a database is created, and the cluster that needs the database gets access to the database. It's all automated.
And now let's get into the demo. What I did prior to this demo, we have a management cluster Sveltos, and the Sveltos dashboard is already installed. And then we have two other clusters. One is going to reflect the services cluster, and the other is going to reflect the cluster who did database services. So let's connect to management cluster. Let's ensure we have project Sveltos installed. It looks good. Now, let's assign a label to our management cluster. We're going to give the label type management only because we want to manage resources within our management cluster using Sveltos. We did that. And now let's create three different namespaces: managed services, Coke, and Pepsi. Effectively, in the managed services namespace, we're going to register the service cluster, and in the other two, Coke and Pepsi, we will install the clusters who need the Postgres database services. Let's ensure the namespace is there. That looks good. And now let's register our cluster where we will install Cloud Native PG. Now here I'm using the Sveltos command line, but you can do that programmatically. So if you define your pipeline or your workflow, there is no prerequisite to go with the Sveltos command line. You can use it via standard manifests. And let's double check that the registration is there and our cluster has been registered. So I can see we have a new services cluster with a type, with a label type services. Let's wait for the agent to be present in the cluster, and then we will continue. Okay, here it is. Now, how are we going to create Cloud Native PG to that cluster? What are we going to use? As seen before, we will use a cluster profile. We're going to say what is the cluster selector. In this case, it's type services. So we're going to match all the clusters who have the label type services. And then we're going to deploy this Helm chart. Now, to deploy the Helm chart, we simply need to apply that manifest file into the management cluster, so the brain of our operation. And once we do that, we have a new cluster profile. And let's see now what Sveltos did in the background. We can see that we have a new Helm chart deployed in our services cluster, that particular version of Cloud Native PG that was deployed a couple of seconds back. Let's connect into the services cluster, and let's see that everything is there. So that's a real view, basically. 10 seconds ago, we had a new pod of Cloud Native PG instance. That looks good to me. Now, what we mentioned in the beginning, we want to provide self-service capabilities to our users. So we're going to use the Sveltos event framework to effectively say, if there is a new cluster that requires Postgres services, so we're going to map or attach a label to that cluster that needs those services. In exchange, Sveltos is going to trigger an event. And if we look here, the destination cluster to install the cluster Cloud Native PG instance is our services cluster in this case. And what we do, we're going to deploy a config map. And then you see the outline of the config map. Effectively, it's again a template that we will dynamically pre-instantiate using the information coming from the management cluster. Now again, I'm going to apply that file to our management cluster. Those resources have been created. And now let's see again how we can bring back to our cluster the connection details of the database plus the credentials. And again, we use a very similar approach as before. We are going to use a Svelte event framework. The event source in this case, it's a secret that has this particular label. And basically, we look for that secret in the cluster, in the services cluster. And then we're going to return back to our management cluster a secret that contains the authentication credentials for the database. And there is also another event that's going to look for a service with that particular label, again in the type services cluster. And we're going to send back to our management cluster a config map that contains the details of the database. So that's a load balancer IP and the listening port. Let's apply that those manifests in our management cluster. And now, what Svelte is doing in the background? Svelte does nothing, right? Because we don't have we did not register a cluster that has a label Postgres required, right? So nothing is happening. So let's go ahead and register a cluster that requires now database services. That cluster name is Coke. That is going to be registered in the Coke namespace, and then we assign the label that we want Postgres required. Once that is noticed by Sveltos, we're going to start creating the cluster Cloud Native PG instance in the type services or the services cluster, bring the credential and connection details back to our management cluster, and then have those resources be ready to be provided to a developer that wants to create a table in our database. Now, let's double check that this is the case. We have the Go cluster, we have the agent, we have the label. Looks good. Let's continue. Let's display the add-ons in the managed services namespace. And what do we expect here to see? A new entry, a new cluster entry. And voila. So we have a new Cloud Native PG cluster instance. And let's connect our services cluster. Let's double check that this is the case. Here you go, dynamically created cluster. Cluster does Coke, because Coke is the name of our managed cluster. That looks good to me. Once we have the cluster ready, what we're going to do, we're going to bring the connection details and the authentication details back to the management cluster. And here we're connected to our management cluster. And look what happened here. We have a new secret and a new config map created a few seconds back. And now if we go into more details, you can see, again, that was a dynamic template. And you can see we have a username and password, basic, secure, and hold it, coming from the services cluster. Same goes for the config map. We will be able to see the load balancer IP and the listening port of our database. So again, Sveltos knew about the information, brought it back to our management cluster, and now we can use those resources. Now, for demo purposes, we're going to assign another label to our cluster, type application, and then we're going to use another set of cluster profile to effectively deploy a job that is going to create a table in the database that we created before. And how that looks like, very similar to what we had before. Again, cluster profile, we're going to match on the type application clusters. We're going to send to that cluster the secret and the config map shown in the previous slide. And then what we're going to do in exchange, we're going to deploy a job that effectively is going to create a new table in that database. So create table to do. And you can read the rest. I don't know if you can, but that's the idea. Let's apply those resources. Okay, so we have a cluster profile and a config map created in our management cluster. And let's check the add-ons in the Coke namespace. Voila, we have a new job in the to-do namespace that created a table in our database. And if we connect to the Coke cluster, I should see at least a job completed. And effectively, that's it. The job has been completed. We created a table in our database. Everything is green, everything is fine. Now the developer can access that table in the database. Cool. Now you've shown a lot of the command line, but also just a side note, Sveltos also has an intuitive dashboard. So In this case, if you don't want to work with a command line, you can also use your dashboard, give it to your teams, assign the correct airbag and service account, and give them access to the Sveltos resources. So a single pane of glass when it comes to Sveltos deployments. Now let's head back to the presentation for the takeaways. My personal takeaways for that session, and I assume Jen Lucas as well, really empower your teams to build meaningful solutions that are able to solve a problem. Stop juggling with different tools that maybe they don't fit your use case or tools that you don't need. And if you use tools like Sveltos, you will be able to deliver faster and with less effort, I would say. Code examples, feel free to scan the QR code. You're going to find all the demo code there.
Yeah, and here we have a few more QR codes if you need it. And I think we have a few minutes left, so yeah, we can go for questions.
Any questions? Yes.
Thank you for the presentation, really nice. I just have one question around the event-driven approach of Sveltos here. Is it like a simple watch between clusters here, or it's a more robust thing? Because I'm just interested to see, let's say, if you miss an event and so on, how Sveltos would, let's say, fall back and recover from that.
Thank you. The way it works is you define what your event is. So you list all your Kubernetes resources that Sveltos has to watch. And Sveltos reacts to those resources changing. And then the way this is communicated back to, so it cannot miss an event because essentially it keeps watching those resources, detects when those resources are changing. Now, to inform the management cluster that an event is happening, Sveltos creates an event report, which is it's a Kubernetes, it's a CRD. So, and the management cluster fetch this resource. So even if you have a connectivity issue between the management cluster and the managed cluster, as soon as the connectivity recovers, Sveltos is going to see and react to it. So essentially you cannot miss it.
Any more questions? Okay.
Hey, thanks for the presentation. Is it a CNCF project? And if so, in which phase is it? Like,
Thank you. No, it's not CNCF yet. I think there is a lot of paperwork to be done there. So I haven't had, we haven't had the time. So it's not there yet, but it's open source. It's all there.
Okay, then if there's no any more questions, you can talk with them later on. Thank you. We will catch up a little bit with our delay, so the break is very short, and we will meet each other again at 11:50 with the next talk. Thanks.
Test. I'm not sure it works. Oh, it does.
Test.
Oh, I just
Test.
Yeah, you need to be a little bit closer. I need to be a little bit closer. Whoops. So let's go with this.
Like this.
Okay.
Go like that. Okay.
A bit higher.
Just don't be shy when you talk. Just say it out loud.
All right. Just
Oh, you already
All
know
right.
new. Yeah, SQI.
so.
Perfect. Top.
All right. Thanks. I think so. Yeah. Like if I talk, people hear me. Maybe like this. Yeah. All right.
Side.
Yeah.
And then it should be perfect.
All right.
I will give you time with 5 minutes, and then you can start to wrap up, and then you have time for the Q&A if you want to do Q&A.
I do. I have like my presentation is around 21 till 25 minutes. So I have my 5 minutes to Q&A. Cool. All right.
But I still give you the slide.
Yeah. No, sure, do that. Yeah, of course.
solve this. Okay, everyone would like to start. Please, if you want to listen or come closer, sit here. And for everybody else, please respect the speaker and yeah, reduce a little bit the volume. Okay, next speaker is Or Navon, and he's going to talk about Argo CD events in combination with Nets. And don't want to take too much time and yeah, point to you. Welcome, Or.
Hello, hey there, everyone. It's really nice being here. I will just share my screen. Whoops. Let's go with that. And let's go. So I'm very excited to be rejected with you all today. Let's get started. So welcome to the Scale Restaurant, a place that serves hundreds of thousands of customers every day. It all started with one chef creating amazing dishes with basic ingredients. As his business grew, he needed to hire more people, and he did so and bought more knife sets and pots and pans. But he forgot to buy one thing. He forgot to buy more cutting boards. And that means that every time anyone needed to cut anything, they needed to wait. That's, my friends, a bottleneck. Today, I'm going to talk about one bottleneck that we had in Honeybook, just like that, and how we solved it. So hi there, my name is Or Navon, and I'm a senior DevOps engineer at Honeybook. I really like board games, and in fact, I'm the board games community lead at Honeybook. I'm also the community lead of Friends of Dorothy, which is an LGBTQ+ community and part of the CNCF communities. And it helps LGBTQ+ professionals to do amazing things, like going to conferences like this and speak, or contribute to open source. It's also part of a broader group called Merge Forward, which is a community that helps underrepresented groups to do those amazing things. So enough about that. Let's get to the context. So meet Honeybook, an all-in-one client flow that helps small businesses to manage their business. We automate everything for them so they will do what they love, which is the reason they open their business. One of the core functionalities in Honeybook is getting our customers paid by their clients. In production, we have our payment service. And once a new client comes in and pay to one of the business owners that we serve, it sends a request to our payment service in production. It then sends a payment request to Stripe, which is the payment third party that we use. And then Stripe sends back webhooks with the status of the payment, if it was approved or rejected and why. That's the situation in production. But what about staging? Well, in staging, we have many dynamic environments, and not only one. And sometimes in peak times, we have around 100 or more dynamic environments running in parallel. All of those dynamic environments need webhooks, and not only from Stripe, but from other integrations as well. So in addition to that, we also have two types of environments in our staging environment, which is preview developer environments, where our developers can create a new environment with the services they want in specific versions to test their stuff. And also E2E environments, which are automatic environments that we create for them before they can merge to main. And in those environments, we run all of the tests and we deploy all of our services. So when we had one dev, like the one chef that I talked about, we had one preview environment that we configured specifically in Stripe. We configured in Stripe specific endpoint that will go to that environment. All of the other preview environments used mocks. And in terms of E2E, we also had one E2E environment that we configured at Stripe to get the webhooks. But that meant that only those environments got the webhooks and all of the other didn't. And that represents our bottleneck. New developer came in. And with new developers, we needed more environments to test those features with Stripe. And also, each integration, like Stripe, has limitations. And in Stripe specifically, the limitation is 16 endpoints, and not more than that. So you might ask me, well, 16 is way more than 1 or 2, right? And you're correct. But first, we have a lot of dynamic environments. And second, it's kind of embarrassing, but one of our principal engineers used a lot of environments for his testing production. By the way, that's the principal engineer. And we understood that we have to create a solution that will distribute all of our webhooks to all of our dynamic environments. So let's talk a bit about our project requirements. First, we want a one-to-many HTTP forwarder. Second, we want it to be observable and lightweight because we want it to be easy to understand what is going on and troubleshoot fast. Third, we want it to be fault tolerance because this is a core functionality at Honeybook and we can't lose any of the webhooks. And third, we want to ensure at least one delivery because our code is idempotent, and if it will get the same webhook twice, it will just ignore one of them. To solve all of those, we tried Nuts. So what is Nuts? Well, Nuts is a message queue written in Go. It's very simple to set up and use. You just run a Nuts container, and you have a message queue. You then can connect to it, subscribe to subjects, and publish to subjects. No other configuration required. That means Zookeeper, well, no more. It also gives us at least one delivery, just as we wanted. And it's a very robust project. In fact, it's a CNCF graduated project. Now, saying robust is great, but we need to understand if it's robust enough for our scale. So what we did was to calculate our scale. So we have around 3 integrations, and we multiply that by around 100 dynamic environments at peak times. And we multiply that by a webhook weight of around 10 kilobytes and in a pace of 1 webhook per second, which is the highest pace in our E2E environments. We get to 3 megabytes per second splitted into 300 requests of 10 kilobytes each. To test it, we created a sandbox environment where we deployed a Nuts server and a Nuts tester. Luckily for us, Nuts comes with a built-in benchmark tool inside the CLI called Nuts Bench that you can use to test it. And that's going to be our first demo. So let's do that. So here I have a namespace with a Nuts server and our publisher that uses the Nuts benchmark CLI. And we're going to run a script called load test that will test our load. Now, I want to test our load for more than just 1 second. I want to test it for 1 minute. So what I'm going to do is sending 18,000 requests all at once and see if it will handle it in less than 60 minutes, in 60 seconds, sorry, which is 1 minute. So let's run it. And we can see it does it really fast. It takes it less than 1 second to deliver all of our webhooks, which is amazing. Cool. So we have the pace that we need. The only issue with Nuts is that it manages everything in memory. And that's an issue because if Nuts will get down from any reason or restarted, we will lose our webhooks. So we need persistency. And luckily for us, Nuts have a built-in persistent engine called Jetstream. Jetstream is very easy to set up and use as well. You just run nuts-js and you have Jetstream. You add a volume and you have persistency. It also gives us a couple of more features above the message queue, which is exactly once delivery, because now we have ACK on every message. It also gives us key value store, and it gives us object store, which is really cool. And we used it. I used it specifically in the past for other other projects. Sorry. It also gives us data retention. So we will be able to save only what we want, the amount of data that we want, and the back in time, specific period of time that we want. And it gives us data deduplication, which is great for cost saving. Cool. So we have a persistency engine. Let's test it. Just like Nuts, we can test the load, but this time with Jetstream. So in the second demo, we have a Jetstream server, just like Nuts, but with -js and the volume. And we're going to load test it and see if it can handle our load. So we can see it also did it amazingly fast using the bench. I will, get it here. Sorry, yeah, a bit larger. So you will be able to see. We did it in around 1 second and in a really amazing pace of 123,000 messages per second. Great, so that's enough. But what will listen to all of the webhooks from Stripe, get them into our Jetstream, and then what will get those webhooks from Jetstream into all of our dynamic environments? So we looked at a few solutions like Airflow and Knative and Tecton, and they can all solve the issue, but they are very complex and they are overkill for our use case. So we saw more interesting solutions, like using Argo events or creating our own solution. Because we already use Argo CD in our production environment, and we really like it, and also Argo events is from the same parent project of Argo, we decided to go with Argo events. So what is Argo events? Well, Argo events is an event-driven workflow automation for Kubernetes. It is built from 3 main components. The first one is the event source, the place that we will get our events from. Those are basically just integrations that are wrapped by the Argo project, the Argo events project. It can be a Slack message or Stripe or even Nuts himself if we want to create a chain. Once we get the event, we can send it to our event bus, which is just a component that wraps a message queue. It can be Kafka or Nuts or Jetstream, just as we need. And once we have this event in our event bus, we can then send it or do whatever we want with it, with the event itself, using sensors and triggers. Once we sense a new event, we can trigger a trigger, and the trigger can be many things, like creating a Kubernetes pod, or executing a Lambda function, or even sending a Slack message. In our use case, we're going to send a plain HTTP request, because that's what we try to do, forward and distribute our HTTP request into all of our dynamic environments. Cool. It also, by the way, Argo events, gives us a couple of more features. So the first one is the one that you see from the right. Just like Argo CD shows us applications and application sets, now in the new version, Argo events shows us the event sources and the triggers and the sensors themselves. It uses the Argo Workflows UI to show it, but we can see it. So that's the thing. It also gives us to filter the events with basic conditions. So we will act upon specific events and not all of them. And it gives us to parameterize our events based on the event content. That means that if you want to get to a specific environment, we can check the event itself and use it to get to the environment. Great. So our initial plan was to collect webhooks using Argo events and get them into all of our dynamic environments and profit. Yeah. If we will look back at the diagram from the start, we will replace the write signal with the Stripe integration event source, because we already get it, so why not? And then we will replace the left question marks with a sensor and an HTTP trigger that will send the HTTP request to all of our dynamic environments, one per environment. Great. Let's test it. As all of the other solutions, we created a sandbox environment with the load tester, the event source, the event bus, and the sensor and trigger. And that's what we're going to do. We will be able to see all of those components here. We have our event source, which is just right now the plain webhook integration of NUTS, the webhook event source. We have our event bus that runs Jetstream, and we have our sensor with a trigger that sends a request by the event that he just subscribed to or got from the subscription to our event bus. Let's run the load test. So while I run the load test, I will say it will take time. It will take more time than what we really need. And I will get back to that later because it will take time. In fact, it took around 350 seconds to get all of the webhooks, and not really all of them, but only part of them, because there is a bottleneck in Argo events. The bottleneck is the sensor. The sensor can sense only 40 requests per second right now if you get only one sensor up. Now, we could optimize it, get more sensors up, but instead, we didn't understand the limitation of 40, and we went with creating our own solution. So we understood that we don't want to go with Argo events, and we go with our solution. So we created two simple Go components. One is the webhook sync, just listening to Stripe, getting everything into a subject in Jetstream that we now manage. And then the webhook forwarder that gets all of the events. We have one forwarder per environment, and it gets all of the webhooks to the specific environment. Cool. Let's test our solution. As you can see, it still runs the Argo events one. In this project, I have the code of like both of them. I build them and then deploy them to the cluster, our sync and forwarder. And let's run the load test. So again, 18,000 requests, sending one time, and we need it to finish in less than 60 seconds. So we will know that it will be able to handle our load. And hopefully, if the demo gods will love me, it will work. And if not, we will get back to the presentation, and I will show you that it usually does work in less than the duration. I'm not sure it will work now. So it does work, and it does that in around those timings. And maybe we'll get it here, or maybe not. But yeah, it works pretty well, and in time and in way less time than what we actually need, which is great. That means that we're ready for higher scale. But there is an issue. You probably already understand it. The issue is that we send currently all of the webhooks to all of the environments. We don't split it so specific environments will get only their webhooks. We don't do that yet. And it was only a matter of time till it will become a problem. And then AI came, and it brought the problem back to the surface. All of our developers created way more features, and way more features went to way more environments. And we got to around 200 environments in parallel. And that created some issues like network issues and services that took more memory and CPU because ignoring webhooks still takes memory. And also our E2E tests took longer because they needed to ignore all of the webhooks. So we understood that we will have to solve it and split the webhooks per environment. And we did so. We changed our services to send a payment request with the environment name itself into Stripe using the metadata of the payment request. It's not only a payment request. There are other resources as well in Stripe, but they are all supporting metadata, which is great. Then Stripe sends the metadata with the webhooks to our webhook sync, and we store all of those webhooks into a specific subject that contains the env name. Once we get it into our JetStream, into the specific subject, we can then subscribe to that specific subject in each namespace. So if our environment is dynamic 1 in namespace dynamic 1, we will get up our service, which is the webhook forwarder, and we will listen only to the subject that contains the name dynamic 1 and get all of those webhooks into our payment service. So we close the loop. We also did one more change, which is to split our webhook sync. So we will have one webhook sync per integration. That's just to handle the load better and have like a deployment for each because each of them has different scale, but Stripe is the largest. And as all of our solutions, we tested it, and hopefully, hopefully, the demo guys will love me today and will get it to work in front of you, and maybe not. We will see. So this time we deploy many namespaces. In each one of them, we deploy an app instance, which is the same as a dynamic environment, and it worked, which is great. So yeah, and in each of those environments, we send 300 webhooks, and then suspected that it will all work in less time and with way less network traffic. And it actually did so. So this is the current solution that we use today, and that's what we did. So what we solved here? First, developers can now test all of the integrations in their dynamic environments. Second, the gap between staging and prod shrank, which is great. And third, now we have the option to run a lot of E2E environments in parallel because all of them get the webhooks. What can we take from this adventure? First, JetStream is a robust message queue, and I recommend using it because it did well in our use case. Second, Argo events is nice for small projects. 40 messages per second is fine, and it's good for small projects. And I will use it because it abstracts a lot of things away. And also, we can optimize it, like you can optimize it to your use case. And third, don't be scared to build it yourself. We went with building it ourselves, and it didn't take long to create all of our services and also test them pretty well, as you saw. So let's connect, and please check out our LGBTQ+ community. We are growing, and thank you. Cool. Any questions? Okay, thanks.
That's good. So we will meet at 12:25 for the next talk. And if you still have questions, or is around, and yeah, see you later. Jed, nice to meet you. You're from the States or you live here? Okay. Which area?
Well, actually, I live in Canada, right? Kind of stuff.
Which area in Canada?
British Columbia.
British Columbia. Okay, that's nice. Okay. I'm from Germany, but I work for Pulumi, which is a Seattle company. So that's I took once the trip because I wanted to experience these little machines.
That's perfect. Yeah, it's a lot. I love
Okay, everyone, please. If you want to listen about kernel observability, this is your chance. So please sit down. We will start. And otherwise, please be mindful with the noise level for our speaker here. And saying speaker, I would like to welcome Jed. He's going to talk about kernel observability. And I just disappear now and give you the stage. Welcome, Jed.
Hello, hello. All right. Thanks for coming. So we're going to talk about kernel observability today. And I think the first question is, what is kernel observability? We will get into that. The quick TLDR is that I'm working for a company called Adara, and what we do is we deploy containers inside of very lightweight micro VMs, which means that each pod that runs in our platform gets its own virtual machine environment. It's a very minimal environment, but it also crucially gets a Linux kernel to run that virtual machine environment. And that's interesting from a security perspective, but it's also interesting from another perspective, which is the observability side. And that's kind of what we're going to be talking about. So bear with me. I just want to give a heads up. I've been up for about 26 hours. I had 2 flights canceled, and I got no sleep on the plane. I'm slightly hallucinating right now. Some of you might actually be real. Some of you might not be. I don't know. But I'm going to pretty much just wing it. So thanks for coming. There might be like 1 or 2 slides that I actually have to like read from my screen because I'm just can't keep all this stuff in my head, and I'm learning this as I go. So thank you. Okay, so we're going to talk about kernel observability, but we're actually going to do that through the lens of AI agents, right? And there's a couple of reasons for that. Like one is AI agents are particularly interesting for us because they're the first time that the industry has really decided that a particular workload is kind of intrinsically untrustworthy, right? Like we don't trust these AI agents, and for good reason. They're non-deterministic. So if you give, 2 AI agents the same input, you're going to get different output with each run. There's no reproducibility, and this is completely ignoring all of the things that are kind of like wacky about AI in terms of, they will basically cheat to achieve an objective. And, that cheating might be compromising your host kernel or escaping a container or, yeeting your credentials into the internet, right? Like the industry has kind of realized that, these aren't just like chatbots, right? Like they're actually like autonomous processes that are executing code, writing to the file system. They have access to all of your credentials. We're very much in the walk and not run part of this. I think eventually we're going to move these agents off of our laptops and into containers into production for a variety of reasons. But just kind of, bear with me and think that we're already there. So, you really can't, from a security perspective, trust an AI agent, right? Like you can't write a security policy because unlike a standard workload where you know how an application behaves, an AI agent is, their behavior space is completely unbound. They will do everything and anything that they can do to achieve the objective, as I mentioned. So again, the industry has kind of come to this consensus that we should run these AI agents inside of like strong sandboxes, right? We should isolate them away from their host because they're effectively untrustworthy. And that's great. And, my company enables that via type 1 hypervisors. Maybe some of you just went and saw our previous talk where we talked about some of the implementation details of how we enable that. What I'm going to be talking about today is like, okay, well, isolation is interesting, but it doesn't really do anything for the developer, right? Like if you're running your container inside of a micro VM, you probably don't know or don't care that you're running it inside of a micro VM. But what makes it interesting for the developer is each of these workloads has a Linux kernel, and that unlocks a huge amount of observability that doesn't exist inside of standard containers today. So standard containers get C groups, which is very limited. So, effectively, like my company allows you to, I'm not sure if any of you run Claude code, you can dangerously skip permissions, right? Like this is running the agent in YOLO mode. This says like, don't ask me permissions to write to my file system, or yes, you can have access to all of my data on my laptop, including like, my taxes and my MRI scan and all of my, GitHub credentials and all that good stuff, right? We want these AI agents to run in dangerously skip permissions YOLO mode because that's what makes them valuable. The more autonomy you give them, the more value you get and the more velocity that you get. But doing so obviously is very dangerous. So that's what Adara does. That's my pitch, is we isolate these agents, put them in untrusted, isolated environments. Yeah, so what we're going to do is we're going to create some CVE slop. So if you take a look at this command, like there's, you can ignore the vast majority of it, but effectively what we're going to do is we're going to run Claude code inside of a container. And in our case, we're going to run that inside of our isolated virtual machine environment. And we're doing some, kind of like scaffolding here to set things up. You'll notice that we are running Claude with dangerously skip permissions. And essentially what we're doing is we're asking this very naive agent to pen test the most battle-tested code on Earth, which is the Go standard library, right? And it's going to generate this pen test report, and presumably we're going to take that slop and file a beg bounty on HackerOne, and I can already hear the curl maintainers crying from here. So let's go ahead and do that. 1 second here. I am going to run this. I don't think I'm sharing both screens, so bear with me here 1 second while I actually can share the right things. Okay, so this is going to run, and this is going to basically invoke a lot of, oh, wonderful. Okay, great. Well, I need to log into my Claude agent here. Okay, well, that might complicate the demo, but for now, we're just going to go back to, something had to go wrong. Okay, so we're going to go back and we'll just kind of walk through the slides then. We might be able to save this a little bit down the road. Okay, cool. So let me actually do with presenter view. Okay, cool. All right, so we've been talking about agents, and one thing that I want to call out is why is this observability interesting? Why is it important? And that's because agents are not microservices, right? Like Kubernetes was designed for microservices, particularly stateless microservices, but agents kind of are completely different for a variety of reasons. So if you think about it from a performance perspective, there's a lot of differences that we're going to call out here. So first off, in the case of a standard workload, you have things like, flat memory, the baseline of the memory just, works just fine. You have proportional CPU, short request, base life cycles. So if you're looking at something like a Grafana dashboard, you know what this pattern looks like, right? AI agents basically break all of these assumptions. So in the case of AI agents, it's all about memory, right? The context window is super crucial. And every file that an AI agent reads, every tool that it calls, every result that it stores inside of its memory, this actually causes memory to grow kind of monotonically. Unlike a web server that handles an HTTP request, allocates some memory for that, and then releases the memory once that HTTP 200 is served and the data gets provided to the user, the AI agent's literally just going to keep on using more and more memory until its context window basically, is consumed fully. So, this looks like a memory leak if you're looking at it from a performance perspective, but it's actually like working as intended. This is the way that, AI agents work. So what we're trying to prevent with this new line of observability is kills, right? So kills are a huge problem in Kubernetes. I saw a thread on Reddit, which of course is probably 100% true, that this person was auditing Kubernetes clusters and noticed that each of the workloads that was deployed into this environment, in this production environment, was about 40 to 50% over provisioned in memory. And they were like, wow, this is extremely wasteful. Like, why are we doing this? And the response that they got back is that, well, an outage, an kill is so expensive for us that we'd rather just pay for the compute up front and just over provision this thing so that it doesn't, basically fall over, which is pretty sad for our industry, especially considering what Kubernetes is supposed to be doing with auto scaling and stuff like that. But this observability, this kernel observability, gives us more insights into what's happening inside of an application so that we can avoid an kill. We can actually know what's happening with the memory in each of our workloads. We can check in on the dashboard, but really quick, I just want to give a little bit of context. We're going to basically go into some stuff that you probably learned years and years ago and forgot once you moved into Kubernetes because, you don't have to think about this stuff, right? We have to think about this because we're working with hypervisors and the kernel and very low-level infrastructure, but Kubernetes abstracts all of this away. But basically in 2007, there was this kind of seminal paper from Ulrich Drepper, and sorry for the butchering of his name, called What Every Programmer Should Know About Memory. And in that paper was this kind of, pyramid of memory that exists on a system. And, basically the entire job of the kernel is to make it seem that you have an infinite amount of memory available to you. And the kernel's job is to make that memory go as fast as possible. So we're going to want to serve data to your application from a register or an L0 cache. We don't want to serve data from an IO device or a hard drive, right? That's going to be very inefficient. So the whole point here is that we want everything to go fast. So what the kernel does is it actually caches all of the data that you ever touch and it stores it in memory. And it keeps that cache because it makes your application go faster. So for example, if you're using a Golang app and it reads a source file, we'll read that file from disk once and then we'll keep it stored in the kernel's cache basically forever until we have to evict that kernel for some reason, or evict that page rather. And the reason why is because it's, the next time something reads it, it's going to be 1,000 to 10,000 times faster based on where that data actually gets served from. So if it's in the kernel's memory cache, then it's tremendously faster. And these are some numbers that were run in 2012 that kind of goes over, what these speeds look like. I'm sure this has changed since 2012, but this is kind of the canonical example. And you can see that an L1 cache reference is half a nanosecond. So if you take a look at the bottom here, we can see that 1 millisecond, which is typically what you measure for, network latency or something like that, is 1,000 microseconds or basically 1 million nanoseconds. So it's super crucial that the kernel does everything in its power to serve data to your application from these much faster, much more expensive areas of cache. And that's going to make a big difference for when we start talking about C groups and what kernel observability enables. Kernel observability is going to give us insight to all of this low-level data that C groups doesn't give us access to. And to illustrate that, I'm going to kind of use Plato's cave allegory here. So if you're not familiar with this, there's a group of prisoners that are chained, and they're facing a wall with shadows that are cast behind the fire, and the prisoners think that these shadows are reality, right? Like this is all they know. They've never actually experienced the real world. C groups is kind of like that, and that's because C groups tells you something, tells you a metric about memory that isn't really relevant. It tells you about the memory free. And going back to the previous slides, we just learned that we don't want memory to be free. We want memory to be cached in the kernel so that the kernel can, serve your application as fast as possible. So memory free is actually memory that's wasted on the system. It's literally just sitting there doing nothing when the kernel should be caching it and making it, highly performant and available to your applications. So in particular, C groups, when you run something like kubectl top pods, it's telling you that you're at like a 78% of limit in your application. But that's 78% of memory that's being used while maybe 10% of that is for your application, and the rest of it's just disk cache that the kernel has cached. This is actually working as intended. C groups doesn't really have any insight into the differences between cached memory, memory available, and memory that's free. So C groups will say, well, we only have 100 megabytes free, but that's actually again really wasteful. So the metric that we care about in kind of like Linux land is mem available. And mem available actually is the much more accurate metric that tells you what the application, what the kernel can do at any given point to serve data to your application. So let's kind of dive into that. So as a developer, you're running a pod. What could you do if every one of your pods had its own dedicated Linux kernel? Not a full VM, like we're running a micro VM. This is a very lightweight environment. You run the same container images, you run the same kubectl. There's no differences to how, the developer ergonomics works in Kubernetes. But you have a kernel, and it's really not that big. It's actually, we measured this, it's about 60 meg overhead, which is actually really incredible that the Linux kernel can run in an environment with 60 meg and give you things like eBPF and scheduling and hardware abstractions and all that good stuff. It's kind of amazing. But with a dedicated kernel, you get something, you get proc mem info. So if you're familiar, proc is basically like a file system that the kernel creates. It's a faux file system, but crucially, that gives you deep granular insights into what an application, what your system could do to make memory available to your application. So I've talked a lot about this. Let's actually take a look at some Grafana dashboards. So what you're seeing here is a Grafana dashboard that we've built at Adara. So every pod that you deploy, you get this dashboard for your application. And this gives you very low-level operating system metrics because each of these pods are running with its own kernel. And you can be able to surmise at any given point, how is my application performing? This is, it's not like trying to replace eBPF. It's actually complementary to it. We can talk about that. But essentially, what you're seeing here is the memory available attribute that I was talking about. And we'll kind of dive into that, and we'll go through a couple of these. You're gonna have to bear with me here because we're going to kind of go into some tech weed or some weeds here. But basically, memory available, you can kind of think about it as like the difference between what your application is using. So it's kind of like mem available is the sum of the free memory and the page cache that's reclaimable. So the kernel, again, it caches everything that it can to make that data available fast. And at any given point, if your application calls malloc and says, I need some memory, the kernel can evict any memory from its page cache to give your application access to that data, right? And that's its job. It wants to make your application run fast. And it has a bunch of algorithms that determines how it does this. So this is also like how kill works. So this is what malloc checks before deciding whether to kill your process. If there's data in the cache that it can evict, then it will evict that cache and then give that memory to your process. If there's not available page cache to evict, then your application is going to get killed. And in C groups, you don't have any insight into this. You only get the memory-free view. So we have the mem available. On the right-hand side here, we actually have a couple of different things. We have, here's the memory available, here's the page cache. So you can actually see at this point that, you know, we have a very low page cache. This kernel hasn't really cached anything at this point. And that's because this container was just instantiated. There's really not that much going on. But let's go ahead and take a look and see what it looks like when we actually run an AI agent. So this is a screenshot of the dashboard that the demo is currently failing with. I apologize, but effectively you would have seen the exact same thing. And what do we see here? We see we have the mem available for, this is the memory that the kernel can provide to our process, our pod, at any given point. And this is from the dedicated Linux kernel that runs per pod in our environment. So this dashboard tells us exactly how the agent behaves during its job. And, you know, basically it sits there running idle. It just waits for you to tell it to do something. And in this case, I did exactly that. I told it to go and, you know, audit the Go standard library and, you know, generate a security report. And when that happens, you can see that there's a dip in the available memory. So we can see here that the mem available takes a dip, and then the cache also takes a dip. And that's because the kernel basically said to be able to give this pod the amount of memory that it needs to do its job, because the agent is doing things like it's forking a bunch of processes, it's reading a bunch of files on disk, it's calling a bunch of APIs to Anthropic, it's doing all of these things. It needs to evict some cache, things that are probably, you know, not very useful to be able to allow this AI agent to go out and pen test the Go standard library. So you can see here that one of the things that we also can highlight is page faults. And page faults are basically when you take memory from the kernel and you actually move that memory and make it available to your application. So your application will page fault and say, I need some memory. And if that happens to be, if that memory already happens to exist in the kernel's cache, the kernel will just map it into your process. Like that's what they call a soft page fault. A hard page fault is what we see here. It's pink, it's at the bottom. It's a major page fault rather. That basically means that the data wasn't available in cache. It was on disk. And if you remember, if you go back to that, you know, what every programmer should know about memory, disk is like 10,000 times slower than memory. So we never want our applications to get memory from disk. We always want the application to get memory from ideally a CPU register, or, you know, barring that, some type of cache that the kernel keeps. So you should pretty much never see major page faults in your application. If you do, that just means that, you know, something's wrong. Like the kernel is trying really hard to provide your application with the memory that it needs, and your application's about to go really slow. And, you know, it's depending on what transpires, it might get killed. So when you run Claude in particular, and I haven't looked at any other AI agents, but it's basically a Node.js binary, and it forks off a bunch of processes. Like it basically just like, you know, creates sub processes and forks out. And that triggered, in this case, all of these page faults when I kicked the job off, which corroborates with when we started the job from the memory available. And this is doing its job. Like, this is basically saying that, the kernel already had all of this data in its cache. So when Claude said, hey, I need to go and read all of these files, the kernel was like, word, I have that data available. Here it is. This is just a minor page fault. We're just going to map this memory into your process, and we're going to go fast. Like, we already have everything cached. The kernel is doing an amazing job. It's making the system highly performant. This is what we want to see. And, zero major faults during that process basically means that all of the data that we need for Claude was able to fit into the 2 gigabytes of memory, or 1 gigabyte of memory that we allocated to this pod, that's exactly what you want. No disk thrashing. So what about when things don't go wrong? So when the kernel has a hard time giving your pod the amount of memory that it needs, well, then it gets killed. And this is what everyone's trying to avoid. This is the outage that people are over provisioning their production compute environments by 40 to 50% for. Like, it hurts my soul knowing that we're wasting that much compute, but it makes sense, right? Like, if you've ever carried the pager, you know that incident response sucks. Like, it's very expensive. You have to, pull in a whole team. You have, an entire process to carry out that incident response. So we want to avoid kill, and that's what the kernel observability enables us to do, because we have these low-level metrics to be able to do that. So let's walk through this. So here's how an kill happens in Kubernetes. And this isn't like the Kubernetes API surface. This is like the operating system kernel low level, what actually happens. So your process calls malloc, which is allocate memory, if you're unfamiliar. And in this case, the kernel can't find any reclaimable memory, right? Like, it has all that memory in cache, and for whatever reason, there's no cache to reclaim at this point. The kernel cannot find memory to give your process. So this is called dirty cache, if you're familiar with this. There's like clean cache and dirty cache. Dirty basically means that the data exists in memory, but it hasn't been written to disk. And remember, disk is slow, and we want to stay away from disk. Disk is awful. So in this case, we're kind of stuck here. So memory available is effectively at 0. And that means that there's no memory available to your system. It's not memory free, it's memory available that matters. So what the kernel does, and this is an oversimplification because algorithms are hard, but it basically scores each of the processes by how much memory they're consuming at any given point. And then it makes a decision on well, this process is using the most memory, so we're going to kill that, which is kind of crazy if you think about that from a multi-tenancy perspective, that your process can get killed because another process ran malloc and the kernel didn't have memory available. Like, it's not that your process asked for malloc and didn't have the memory available to it. Another process did, and your process could just magically and mysteriously get killed. It's kind of wild, but that's just the way that it works. So one thing that I wanted to call out here is that if we go back to our AI agent example, kills are catastrophic. And we talked about how people are over provisioning their production environments by 40 to 50%. But if you think about it, those are just like stateless web apps. Like, if an kill happens for a front-end service, all we have to do is just relaunch a replica, and then the HTTP request gets routed to the new pod. That's not how AI agents work. You tell it to do something, and if you tell it a sufficiently advanced thing, it takes 30 to 45 minutes, maybe multiple hours, to carry out some type of complex job. And there's a bunch of state that is stored in that agent's environment that's catastrophic if it gets lost, because that kill basically, you've wasted all of that compute, you've wasted all that reasoning. There is no we can pick up from here. It's just you have to restart from scratch. So kills are particularly pernicious in the case of AI agents, but this is probably true with any stateful workload as well. Okay, So I'm getting close to needing to wrap up here, so I'm just going to show you a quick matrix of what type of metrics are available to the kernel versus metrics that are available to C groups. And you can see here that mem available, the key metric that we've been using to identify is this process about to get killed, how much memory does it actually have available to it. That doesn't exist in C groups. Not even C groups v2, which Kubernetes just moved over to. That only exists in the kernel. And if you look at it from a node's kernel, if you don't have a dedicated kernel, you're only going to get mem available for the entire node. It has no idea what a container is. That's just a completely different abstraction. Reclaimable memory, we've kind of talked about this as well. There's no C groups support for reclaimable memory. That's only the Linux kernel that tracks this. So you have to have a dedicated kernel to be able to identify how much memory you can reclaim to give your application. The amount of processes that are running, any IO scheduler stuff, only the Linux kernel can tell you about these things. And this list is pitifully small. If you take a look at the Linux kernel, like just traverse proc and look at all the crazy metrics and counters and accounting that the Linux kernel does on the system, it's baffling how much data is available to the kernel versus C groups, which there's nothing wrong with C groups. It's the abstraction that we have, but it's very limited. It's only telling you the memory that's free, which again is going back to my example. That's a lie. Like the memory free is a completely it's a vacuous metric. It's vapid. It doesn't mean anything. Okay, cool. And then page faults. The thing that I was showing, just to give C groups props, they do have page faults. They have page fault support per workload. So the TLDR for this talk is more data is better. Observability, you always want better, richer, more low-level data for your observability. And the only way that you can get that is, if you do the hard work and make that data available to your observability pipeline. That's what we're trying to do at Adara, is we are basically, anyone can do this that, runs micro VMs, right? Kata can do this, but the idea is that when you run containers in this new kind of paradigm of micro VMs, you get a tremendous amount of additional observability. And you can do things like avoid unkills. You can understand exactly how much memory your application is needing or using at any given point. The only question is like, what are we going to do with these metrics, right? Like, how will you make use of these low-level metrics that C groups isn't giving you? That's it.
Any questions? Everybody's hungry. This is your chance. Otherwise, yeah, you can talk. Hey, perfect.
I've run Kubernetes on VMware, and I noticed that our clusters were using, like, say, 30–40% of the memory allocated to it, and the rest VMware was just using for other tasks. Maybe you can explain a little bit about that.
To be able to say that I don't know anything about VMware, but I worked for a company called Heptio, and Heptio got acquired by VMware. So unfortunately, I do know some things about it. Yeah, I mean, I think that's probably just the old world of VMs colliding with the new world of containers, right? Like, I think that's the real challenge that we've had at Adara, is to try to get that right. Like, we want the developer ergonomics, we want the performance efficiencies of containers. We just want to run them as virtual machines. And from my personal perspective, I have to be very careful because I know this is being recorded, but I think that VMware maybe didn't understand or didn't have that balance right. I think that they tried to kind of like take containers and shove it into an existing VM mindset that made VMware very successful over the years. So, for example, VMware did not create micro VMs. They didn't launch pods inside of dedicated VMs. They kind of just, gave you the ability to spin up nodes as VMs, which doesn't really solve the fundamental problem that we're talking about here. And it doesn't, play nice with things like, auto scaling and C groups and all the other stuff. So I hope that that's a reasonable answer, but I think that it's kind of like, hypervisor from the 90s era colliding with newfangled cloud native technology. I think there was another question as well. I think he was.
Thanks, and thanks a lot for the presentation. I have a quick question. I'm a maintainer of an operating system, Flatcar, and I would like to know if we need to enable some specific kernel parameters to enable those observability metrics, or if it's available by default when you boot the kernel.
That is a great question. I absolutely love that question. Thank you. Yeah, so what's interesting is that the way that we do kernels is we build from upstream kernel.org, and then we put them into an OCI image, and then we ship them out as a container image. So when you run a workload on our platform, you actually do 2 image pulls. You do an image pull for the kernel, and then you do an image pull for your application container. So in that case, like, we are kind of defining what gets what the build steps are for the kernel. But at some point in the future, maybe we have an integration with Flatcar, and I would absolutely love for more people in cloud native to start thinking about what can I do from the kernel's perspective to start giving better, richer, more valuable observability. I know you had one more question too.
Yeah, thank you. As a quick question, on the security perspective, now that you're running the kernel on the container, everything, the containers need to be configured in privileged mode to make that possible? I mean, now because agents, yeah, the use case, your use case was like a running agent on the container, and now I'm thinking agents in a privileged root access container, right? Right.
Great question. So you can run anything in our containers. It's just a VM. Like, we're not opinionated. You can run privileged. The key thing is that if you run privileged and then that workload gets compromised, it's contained to that one virtual machine. So instead of privileged today, where if I get privileged, I can read memory from any other pod. If you get privileged inside of we call it a zone, but if you get a privilege inside of one of our pods, you only get privilege for that kernel, which only gives you access to privileged for that pod. So it's kind of like a huge reduction in ambient privileges that you would get with the standard environment. So that's kind of how we enable that from a security perspective.
Okay, small question. Say, for example, and this is really nice because you actually have confidential containers and that kind of stuff. That comes with free observability. Say I would like to have the observability for the containers, but not running microkernels. Couldn't I do this by extending the C groups or using eBPF or something like it? Because
I was really hoping I'd get an eBPF question because shout out to Isovalent, used to work there, love eBPF. I wrote a book on eBPF, go buy it. Just kidding. No, eBPF is not, it's not a competitor to this. We isolate the eBPF data. So today when you run eBPF, it's a shared kernel and you get data from the entire node, and then you have to basically do a bunch of filtering to get what data that you're interested in. If you get a Linux kernel per workload, you can run any eBPF programs, and it's only going to be relevant to your specific application. So more eBPF is good, and more observability is good. I'm not advocating that we throw away eBPF. I'm saying let's bring eBPF into this model, which we've already done. We support Falco, which is a good start, but we need to support Tetragon and all the other kind of eBPF agents. So yes, yes, and we definitely want to support that. Thank you, everyone.
Okay, thank you. Lunchtime. See ya.
Hello, everyone. We're gonna start, and we have Tomasz on the stage. I was gonna say screen, but it's also a screen. So please come by, and if you can make it a bit quieter at the back, would be great. So take it away.
Thank you. Hi, everyone. I'm Tomasz Tarczyński. I'm a customer reliability engineer with Isovalent, which is now part of Cisco. I'm gonna talk today about Kubernetes networking and implementing Kubernetes services without kube proxy. So how to remove kube proxy from your cluster with Cilium. What we are gonna talk today about. First, we'll start with a very short introduction into Kubernetes services, how those work, so the very basics, then how it is implemented with kube proxy using IP tables mode, and then we'll jump into implementation in Cilium with kube proxy replacement. Just 1 second, please. Okay. So Kubernetes services, a very, very short introduction. We will be interested into two main types of Kubernetes services. So one use case is for handling the east-west traffic. So that's the case when we have a client application running within a pod, within a cluster, and then that client application needs to connect to a different application within the same cluster. So to do load balancing between different application pods, as we can see here, we need load balancing done with a service of type cluster IP. This is implemented by having a virtual IP address available within our cluster to all the pods there. What's important to us about this kind of service is that this is reachable only from within the cluster if we have a cluster IP. And then the second type, we will look into is a node port. So that's for north-south connectivity. We have, again, our application pods within our cluster, but the client runs outside of the cluster. So we need traffic to enter into our cluster. That's done by exposing a static port on each of the nodes of the cluster, so that we can make this service reachable from the outside. So that's just the very basic, what we need to know about Kubernetes services, to then look into how they are implemented in those two different ways. First, we will check how this is done with the standard kube proxy in IP tables mode. Here we can see the packet flow through IP tables in the Linux kernel. It is quite a complicated view, but what is really important for us is that we have 4 different tables on the top there, and then all the different chains within the kernel within IP tables, like pre-routing, input, and so on. But for our use case, for implementing load balancing and implementing services, we are interested only in the NAT table, which is responsible for network address translation. And as a next step, we will simplify it a little bit further still. So this shows how a packet flows through the Linux kernel and how it is processed by IP tables. So we can see a packet entering the node as ingress, then going through pre-routing, a routing decision, and then depending if its destination is local process or not, it can go, for example, to post-routing and exit the node. And actually, for this talk, for Kubernetes service implementation, we are interested only about this forwarding path. So in effect, we are looking only at the NAT table, IP tables, and only those 2 chains within that table, so pre-routing and post-routing. So that would be our focus when checking how it really works. KubeProxy, where it lives within our cluster. So we have a bunch of Kubernetes nodes, worker nodes. There is control plane as well. But on each of the worker nodes, what's important to us, there is kubelet, which runs our containers, our pods, and there is KubeProxy that implements the services load balancing. So it connects to Kubernetes API, and based on the information from there, implements the services on each node individually. Now, we will dive deep into how this actually works, how this implementation is actually done with IP tables with KubeProxy. So we have a test cluster here, just a simple kind cluster with 2 worker nodes. And we will examine in detail how services are implemented. So on each of the nodes, as you can see, we have KubeProxy pods running there. That's how our setup looks like so far. We have those 2 worker nodes connected with an underlying network. And now let's implement a cluster IP service on that cluster. So we are running a very simple Nginx deployment with just 2 pods, 1 pod on each of the worker nodes, and then expose it with a service of type cluster IP. We can see the service virtual IP displayed there. It's exposed on port 80, and it has 2 endpoints, so the 2 IPs of our worker nodes. So far, so good. Now let's send some traffic to that service. So we have another client pod netroot in the same cluster, and we send requests to the Nginx service. And what we can observe is that we get responses from the two pods that are backing our service. So it gets responses randomly from either the first or the second pod. How this is actually implemented. So the setup that I've shown so far, we have the two application Nginx pods, the client pod on one of the worker nodes, and then the netroot pod. It talks to the virtual IP address of the cluster IP service. And the implementation of that, it's done in IP tables. So it will go through the different chains, different rules. It hits the pre-routing chain, then there is a match made based on the destination IP. So if destination is our virtual IP, then we redirect that traffic. We do destination NAT, network address translation, to either of the backing pods. So either the left-hand side one or the other one. And it's like 50% probability of hitting each of those. And now how those rules look like exactly. I will go through that rather quickly, as that's a lot of rules, but we have our pre-routing chain, which forwards processing to the kube services chain. From there, we do a destination match. So if destination is our service virtual IP address and port 80, then we forward processing to a specific kube service chain. In that specific kube service chain, we have two rules for the two service endpoints. So those are related to our two pods that are backing the service. And the forwarding is done with, again, 50% probability of hitting the first of the backends or the second. And then at the end, we have those two kube service endpoint chains, which do the actual destination network address translation. So the DNAT rules are there, and the traffic is actually DNATed to the specific IP addresses of the backing pods. So those were the IP tables rules that implement what we have described here. Let's test it really quickly. So we have our two pods, and then we run 10 requests to our Nginx service. We get responses randomly from the two backend pods. And then checking again our long list of IP tables rules, we can see how the counters are growing. So we had 10 connections that hit kube services chain, and then the two different endpoint chains were hit by 4 connections for the first one and 6 for the other one. Let's look quickly at scalability. So what if we do a deployment with 20 pods and then expose it with 1,000 of services? So we create those 1,000 services and then check how many IP tables rules do we have as a result of that. So for kube service rules, we have 23,000 of those, and then kube service endpoint, 80,000 of such rules. So scalability of it, it's like we could end up with a really, really long list of IP tables rules that then need all to be processed for each packet going through the kernel. So it results in some possible scalability performance issues. There is the other case that we introduced, so a node port, so north-south kind of traffic. For this one, I will just describe it quickly how it's implemented with kubeproxy and IP tables. So we have our two Nginx pods running in the cluster. There is a client that sits outside of those nodes, and that client, it then connects to a node port service by connecting to the IP address of one of the worker nodes on the static port, so 3280 in this example. And the implementation of that in IP tables, again, we have our pre-routing chain. In that chain, we match traffic that has the destination of our local node. Then destination port is TCP 3280 in this example. Then we do destination NAT, so rewrite the destination address to redirect it to either of the backing pods. Then we also need to do post-routing to also modify the source IP addresses. So in this case, we do masquerade and do source network address translation to use the IP address of the given node as a source address of that traffic when it's redirected. And that's because if we go from one node to another with that traffic, that other node, the destination needs to know where to send the replies to. So that's why SNAT or masquerade is needed as well. I will not go into all the IP tables rules in that example, but you can imagine that's even more. But instead of that, let's jump into how it can be done with eBPF. So a very short introduction into eBPF, the technology that Cilium uses under the hood to implement all its logic, all its data path processing of the networking traffic. So what eBPF does, it allows us to program, to modify Linux kernel behavior and how it reacts to certain events. Those eBPF programs can be attached to different hooks in the kernel. So those different points where we can attach our eBPF programs are, for example, the two that will be interesting to us in this presentation, either system calls or to events on network device level, packet level events. So how the kernel processes networking packets. It can be modified and programmed. How it's done specifically in Cilium. So again, how eBPF works, how it's implemented in Cilium. The right-hand side is kernel space. The left-hand side is user space. So there is this distinction within Linux that there are our programs that run in user space, but there is also the whole kernel space below that. So Cilium agent is a process running in the user space. And for what we talk about here, the two main functions of it that we are interested in is first, that it loads the eBPF programs into the Linux kernel. In the kernel, they are then verified by eBPF verifier, compiled to the native code, and run there. And Cilium agent also writes the contents of eBPF maps, which are basically a configuration for those eBPF programs. So thinking about services implementation, your service logic definition needs to be configured, what kinds of translation you want to do. That's stored in eBPF maps. And then the eBPF programs read those maps and apply the Cilium data path logic within the kernel to all the traffic coming to such node. And the very basic overview of Cilium's architecture. So on a given node, what we have here is a Cilium agent pod, which runs in the user space. It watches Kubernetes API for different kinds of objects, like pods, endpoints, services, so all those objects related to how we handle network traffic. Based on those information from Kubernetes API, it then programs the eBPF data path in the kernel space. So in that way, we can have, for example, our service logic implemented on each of the nodes. So let's see how Cilium implements the services logic with kubeproxy replacement. So how it can be done in eBPF. Again, we have our test cluster configured slightly differently. We removed kubeproxy from that cluster. Again, 2 worker nodes. And on those nodes, we have the Cilium agent pods running. Yep. Oh, yep. Okay. Yep. So the Cilium agent pods on each of the nodes. And what we can see here as well is that we don't have kubeproxy running in that cluster. And then let's start with a cluster IP service again and how it is implemented in such a setup. So again, we have our 2 Nginx pods exposed as previously with a cluster IP service. We can again send some traffic and get responses from either of the pods. But then if we check our IP tables rules for the same chains that were used before, we can simply see that there are not such IP tables rules in that cluster. So let's look into how this is actually implemented. Same setup as before, 2 Nginx pods, 1 Netshoot client pod, connecting to the virtual IP of the cluster IP service. And then the logic this time is implemented in eBPF, not in IP tables. So we have the syscalls hook within the kernel. The logic that we are programming is triggered by 3 different syscalls. So either connect or send message or receive message. For those syscalls, we want to match the destination IP of the cluster IP of the service. And then we do load balancing, but on the socket level. So basically our socket configuration is modified just when those sockets are created to rewrite the destination addresses so that they are one of either of the pods that back those services. Here we can see Cilium configuration that enables this. So first, we have kubeproxy replacement enabled in this cluster with socket LB enabled as well. And we have 2 kinds of services implemented with kubeproxy replacement, which are cluster IP and node port. Checking how this looks like exactly from Cilium's perspective. So we have a cluster IP service, the view of it from the Cilium agents perspective, there is the virtual IP of the service, which then redirects our traffic to the two backend pods. And we can also see the configuration in eBPF maps that is stored in the kernel space. So we can see the network translation logic here. So our service virtual IP address is translated to either of the two backend pods, and that's a cluster IP service, as we can see. Here we again make 10 calls to our service, 10 different connections. And let's see what it results with within that client pod, actually. So within the Netshoot client pod, we look at socket statistics. So how the networking sockets look like within that pod. So we have 10 sockets that were just closed a moment ago because we've already made those connections. But what we can see here is that the destination addresses of those connections, they are already the IP addresses of our Nginx backend pods. So what that means is that the actual translation of the addresses was made already on the socket level. So when the application connected to the service IP, it was translated already at that point, and the actual network traffic, actual network packets were already using the destination IPs of the two backing pods. Yep. Okay, so the question was, why do we see 10 different entries here in the list of closed sockets? And that's because we've just made 10 different connections, and then each of the closed sockets, it corresponds to one of those connections. So we had 10 connections and 10 closed sockets. So that's the implementation again. And the last bit about it, we also have observability, which is enabled by Cilium's eBPF implementation of this. So what we can do, we can use Hubble, which is a command line tool that comes with Cilium, and it enables you to watch the network traffic as it flows through your cluster. So in this specific case, we can see the network address translation for our connections from the Netshoot client to the Nginx service. Then it's translated to one of the Nginx backing pods. And then we can see all the connection states, how the connection progressed through those states. We then have a node port case. I will go quickly through that because we are already running out of time. So pretty much the same setup, but the type of service is node port. We are able to query the same way as previously. The client is outside of the nodes. And this is again done in eBPF in the traffic with the traffic control eBPF hook. We do, again, a match is done for the destination port of the traffic, then destination NAT is applied, and then masquerade again, so that if the traffic goes from one node to another, we also need to do source address translation. I'll skip the details of how it's exactly done. Just, yeah, another kind of service, a node port. And as we are already running out of time, so let's summarize what we've seen here. We've done life of a packet kind of look into how services are implemented with kubeproxy and IP tables, and then how it's done with Cilium and eBPF. And the basic comparison between these two, it is like with kubeproxy. We use netfilter and IP tables for that. The service state in that case is encoded in rule chains. The evaluation of that, it's a sequential evaluation. So we need to go through whole chain one by one. And then updates, they require a bulk rewrite of the whole rule chain. In comparison, we have eBPF implementation with Cilium. So it uses eBPF programs and maps. The state is stored in hash maps. This uses hash map lookup, which is way more efficient. It's way lower complexity to compute that, to go through that. And then updates can be done to only the individual affected entries in those maps. So also more efficient to update that. Just a bunch of reference material. So the first one is the whole demo that I showed. Like if you want to play with that, it's available on GitHub. How kubeproxy replacement works with Cilium, it is documented in our Cilium documentation. And there were a few other talks before where my colleagues also talked about this. Yep.
We don't have time for questions, unfortunately.
Okay, so that's it.
Thank you, Thomas.
Thank you so much for listening.
You can find Thomas in the hallway afterwards. Yeah, thank you very much. We have a 5 minutes break and we're gonna do the next one.
Thank you.
You were in Sofia, right?
Sorry?
You were in Sofia at my meetup before now. back, please, can you respect the speaker's time to present? Thank you very much. If you can be a little bit quieter, would be great. Take it away.
Thank you. So, hi everybody. I'm Yannick. I'm from Bern. I work at a small consulting company in Bern called Bespinion, and we help our customers move their applications into the cloud by modernizing them. And by cloud, I mean most of the time Kubernetes or AWS, GCP, or Azure. So before I start, I'm not used to speaking into a microphone. So if I fail, please tell me if I have to wide away or whatever. And yeah, another quick survey I want to do. Please hands up for those that know about chaos engineering or actually did some. Oh, wow. Okay. And again, hands up for those who know about Rust or have used Rust. A bit fewer hands, but that's okay. So yeah, I will first in this talk, I will talk about chaos engineering. We'll go through some API designs. And after that, I'll show you a example implementation in Rust, how we can implement chaos. So before I start, I was inspired by this talk when I was attending last year's Swiss Cloud Native Day. The Swiss Cloud Native Day is an annual conference hosted in Bern by the local Cloud Native meetup. Also, one of the speakers after me attended this talk and gave a talk there. Not attended this talk, but gave a talk at Swiss Cloud Native Day, which was also quite interesting about how to create your own Kubernetes distribution by Ben. And I was sitting or attending this talk here from Ty, engineering manager at Datadog, about how they implemented chaos engineering in their organization. But the talk was not really focused on the technical side. It was more focused on the organizational development aspect of chaos engineering, which is also a huge topic. And also, as Ty did a presentation in its own. But I was attending this talk, and after this talk, I was really mesmerized by the idea of how can I actually intentionally disturb my workload on Kubernetes. And then I went down the rabbit hole, and out came this talk, more or less. So before we dive into chaos engineering, here's a definition of it by the chaos community from 2015. So chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production, which means we actually want to train or prepare ourselves for the worst case scenario, so to speak, and in the end get more confidence in our systems. And for me, one of the first touch points with chaos engineering was actually in 2012 when Netflix open sourced Chaos Monkey. And we've gone a long way since Chaos Monkey, especially when you take a look at the CNCF landscape. So when you go to the CNCF landscape and filter by the CNCF projects, you will find these 4 projects in the chaos engineering bracket. So there's Chaos Mesh, Litmus, Chaos Blade, and Kraken. For this talk, I will focus on Chaos Mesh and Litmus when it comes to the API design. Here are some facts about them. So you can see they're not really that new projects. They both got donated to the CNCF in 2020. And since then moved to an incubating stage, so they have a bit more traction or adopted in more companies. And yeah, both projects more or less the same age if you count the age as a CNCF project. And both of those projects offer you a huge choice of experiments you can run on your clusters, or not even only on your clusters. For example, types of chaos they provide is pod chaos, pod network chaos. There's also node chaos you can simulate, and even more application implementation specific types of chaos like Spring Boot chaos or JVM chaos. And if you want to go below the cluster, more or less, then there's also cloud infrastructure chaos that you can provoke. For example, randomly rebooting an EC2 instance if you want to. And there's lots and lots of more experiments and, again, kinds of chaos they provide. For this talk specifically, we're going to take a look at pod chaos, which will be delete the pod, a random pod, and then also terminate random containers. And then we'll also take a look at pod network chaos, specifically packet loss. So this is the first example of how you use the APIs of Chaos Mesh and Chaos Engine. On the left-hand side, you can see the Chaos Mesh definition of a pod chaos. On the right-hand side, you can see how you orchestrate chaos using Litmus. And as you can see, Chaos Mesh provides us a CRD, a specific CRD called pod chaos to define our pod chaos, where Litmus took a more general approach, I would say, to how the API is designed. In Litmus, you don't create pod chaos directly. You configure the chaos engine to create pod chaos or to run a pod chaos experiment. You can see, so when we quickly go through the definition here, so you can see in Chaos Mesh, in the spec, we define the action of pod chaos that we want to do. Here it's a pod kill. Then we also specify the mode. One means just take a random pod that is being selected by the selector below. In Chaos and in Litmus, we have more or less the same structure. We have an app info where we select which app that we want to target. And we just give it an experiment, or we add an experiment to the experiments list that we want to run called pod delete. And we configure that experiment not through the spec directly, but by specifying an env-var. For example, here we say we want to force delete the pod, the random pod. Here's the same for terminating a container. In Chaos Mesh, what changed is we have a new action selected, which is called container kill. And we also, when we use a pod chaos, then we also need to specify which containers we target. So here we target an Nginx container, or the container called Nginx. And more or less the same configuration for Litmus. Here, as you can see, we specify an env-var where we specify which container we target of the selected pods from the deployment with the label app equals Nginx. And here's the last example, how you can use the API directly for both projects. As you can see, Chaos Mesh follows through with their API design decision to actually have specific or providing specific CRDs that you can use. So in Chaos Mesh, you get a network chaos kind, where you can specify what kind of network chaos you want to create. Here, what we do is we want to have packet loss, and the direction is 2, so we have egress packet loss. And again, this time we don't want to target just a random pod, but we want actually to target all pods. And yeah, there also we specify the loss, how many percent or how much percentage we want to lose of packets. And again, the same in Litmus. In Litmus, we have pod network loss as an experiment we can use. And we configure that pod network loss with network packet loss percentage env-var of 50. So this should give you a small overview. Keep in mind, it's just my outside perspective on those API design decisions, and I'm not here to like compare them against each other. but you can see there's one more specific, like I would call it more Kubernetes-ish design choice in Chaos mesh, where you actually have different kinds of network or pod chaos or just different custom resource definitions. And Litmus followed through with a more general approach of having a chaos engine and then configuring that chaos engine. Both of them have their pros and cons, of course. But yeah, that's more or less about the API design here. So let's build our own, because when I see those API design decisions and all those APIs, I'm just asking myself, how actually does it work behind the scenes? And for that, I prepared some demo toy chaos controller called Keris, or I call it Keris. It's written in Rust. The reason for Rust, or I don't really have a specific reason to use Rust here. It was just for my personal curiosity, how you can actually use Rust to create a Kubernetes controller. And in the implementation, I've used, or the most important crates I used, these are the libraries that you can use in Rust, the external libraries. I've used the Kube library to interact with Kubernetes and also write a controller. I've also used Tonic, which makes it really handy to create a gRPC client and gRPC server through protobuf definitions. And I've also used this error, or want to show this error or highlight this error, because it really helps out with error creation and error ergonomics. And Keris will support pod chaos and network chaos. Also, in terms of CNCF projects that I've used, the Kube crate is an official CNCF project. It got donated in 2022. And it's now, the current release is now 3.1, which was published this week. The 1.0 release, although it didn't really matter because the crate was quite stable before the 1.0 release. But if you're interested in 1.0 releases, it was last year. And the Kube crate provides us, in an abstract way, three things. It provides us a Rust client to interact with Kubernetes, a generic typed client we can use. Then we also get a runtime abstraction, or some runtime abstractions that we can use, heavily inspired by controller runtime. And then also we get a derive macro we can use to generate our CRDs and everything that we need to have our own custom resource definitions. And when we deep into the code, this is more or less the most important definition or function signature that I've used. It's the definition for a reconcile function. And you can see here, even though you may not be familiar with Rust, you can see it expects two parameters which are generic. The first one will be the object that we reconcile. So it will depend on which API we reconcile. It will be our own, of course, for our own CRDs. And the second one is a context, which is also generic, that we can define by our own and provide, for example, gRPC clients or whatever we need for a reconciliation. And it returns a result, which will be either a reconcile action or an error. The reconcile action would be, for example, to requeue another reconciliation, or an error would be something failed and now has to be handled by an error policy. This is the overview of the architecture of Keris. We have two important parts. We have a controller, which of course will reconcile our CRDs. And we also have a daemon, an agent that is deployed on the node. And the reason for that is we need to actually interact with the container runtime. For this example, I just focused on containerd because everything runs in a kind cluster, and containerd is the default, or I think at the moment, the only container runtime supported by kind. And we also need access to the node to inject network chaos inside of the pod network namespace or the container network namespace of the pods. So as you can see, I took really a lot of inspiration by Chaos Mesh, but I also think it makes a better demo to have multiple CRDs that we reconcile. This is the first one. It's also called Pod Chaos, and it also supports actions, two kinds of actions, a pod kill and a container kill. And it also supports a Kubernetes selector to select those pods that we want to either the pod get killed or the container get killed of one of those pods. For the implementation, what I do or what I don't really show on this slide is we will always select a random pod through this selector. And if it's a container kill, we also select a random container of that pod. And we do that every 30 seconds. So this will get us some chaos. So let's see. Hopefully this works. So here you can see the demo environment. Thank you. First, there's the overview of what I deployed on my kind cluster. First, we have this Keris system where everything lives in of Keris. We have the Keris controller as a deployment, and we have a daemon set, which deploys our Keris daemon to all the nodes we need to. I've also defined a headless service called daemon in this namespace, which is used to find out which agent to connect to in the cluster. I do this using the endpoint slice resource, where I get a mapping from all the node names to the node IP addresses where the daemon set is deployed to. And just a side note, the daemon set, of course, is deployed as a privileged pod. It also has capability network admin because we want to do shenanigans with the networking on the node or on the of the pods. And yeah, that's more or less about it. Maybe the daemon also has host pid set to true because we also need access to the process IDs of the host, because we want to interact with the processes running as contained processes directly. So here's the demo for Pod Chaos. Maybe is the font size big enough for you? Okay. So I've deployed in the default namespace, I've deployed an Nginx deployment with 3 replicas. Let's take a look at all those pods. And the first thing I want to deploy is the pod kill chaos, which you can see is just the one from the slides. And I will apply them, and you can see what will happen. Of course, the pod kill is the easiest example, more or less, in this demo. So I apply it. And now it's really fast because the reconciliation happens more or less immediately. So it just immediately deleted a random pod. And you can see that here in the age. So before it was more or less 33 minutes, and now the first pod in this list got deleted. I can also go a bit more below the API, the Kubernetes API, or what Kubernetes exposes to us, how we can do some stuff with the pods. And I will apply or override wait a minute, container kill. I will override the pod chaos that I have applied before, and instead of the action pod kill, I will do a container kill, so we can see how the system handles it there. Now you can see, by random chance, it targeted our first pod again. And now the first pod is, instead of being recreated, it was restarted. And this will go on for however long we apply this pod chaos as I implemented the demo. So these are the two kinds of pod chaos that carriers can do. So let's take a look into the implementation at the code, how it's done. Here we are in the Rust module that provides us the controller to reconcile pod chaos. And one thing I want to highlight is how I actually defined the CRD. Here you can see I just had to write a struct called pod chaos spec. So I defined the spec, the specification of a pod chaos, and I've used the cube macro, the derive macro here up there, which then generates me everything else around the spec of the pod chaos. And here I can specify everything I need to. For example, the plural, or if the resource is namespaced or not. And behind the scenes, the struct pod chaos then gets generated by this Rust macro. So it actually generates a valid AST out of that, and then adds it to the compilation, of course. And when we take a look how it's implemented or initialized first, it's below here. Here you can see I create a new controller. This is the runtime abstraction provided by the kube crate. I specify a reconcile function for this controller. If you take a look at the signature, you can see it's the same signature, not generally generic in this time, but specific to the pod chaos that I mentioned before. When we take a look what's defined there, it's just a function, and then it calls the reconcile function of the pod chaos itself. This is just a pattern that I found in the examples of the kube crate, and I really liked it, and this is why I also did it like that. If we take a look into the reconcile, of course, first we have to decide what kind of action we want to reconcile. And here I just do a pattern matching on the action, which is itself an enum. And if it's a pod kill, we do a reconcile pod kill. If it's a container kill, we do a reconcile container kill. So for the pod kill, nothing special here. Probably you also already get how it works without actually showing the code. But here, just to be complete, we select a random pod. This will use the rand crate and just select or use the Kubernetes API with the label selector that I specified to get us the pods. And it will select a random pod. Of course, this pod could be optional if we don't have any pods matching the selector. So here I just see if it's there or not. And yeah, later on we access using, again, the kube crate, we access the pod API, and then we just delete the pod that we randomly selected. Really easy. So if we want to go a bit more below that, we do have to do some more stuff, of course. And this is happening in container kill, and it will also happen in network chaos. Here again, in container kill, we select a random pod. Of that random pod, we need the node name, where it's scheduled on, to find out which agent we have to talk to do something with this pod or with the container of the pod. We get a target container through the status field, and we choose a random container status where it gets us in the end a random container ID we can use. And this container ID actually is also used internally to reference the container scheduled by the container runtime. We will strip the container D prefix, and then the fun part begins. We get a daemon client from the context with the help of the target node name, the node name where the pod is scheduled on. And then we'll get a gRPC client actually to be able to specify a kill container request. And I will show you later how the daemon is implemented. It's really small implementation. But first, before we go into the daemon, I want to show you, or I want to say something about traffic control. because it's really important to understand how network chaos can be simulated and what I actually used to do it. And for that, I use traffic control, which is a Linux util provided by the IP route 2 package or IP route package, depending on your distribution. And with traffic control, if you're a seasoned veteran Linux sysadmin, you probably will have used traffic control already. For me, it was new because I have a software engineering background and I wasn't really interested in providing quality of service stuff for my laptop or my network. But with traffic control, you can essentially control how the Linux kernel can send packets, more or less, in an abstract, really abstract way. And one thing you can do is you can queue disciplines, these queue disks. And with queue disks, you can actually do a bunch of things. You can, for example, limit bandwidth. You can prioritize traffic. You can police packets, so you can mark them and then filter them out with IP tables, for example. Or you can use NetDem, the NetDem queue disk, to simulate unreliable networks. And of course, Keris uses NetDem to do that. And on the right-hand side here, you can see how Keris actually uses NetDem. It's just a TCQ disk, and we add one to the network interface ETH0. We assume we have one, and it's called ETH0. And we add the network emulation of a loss of 50% to it. And to remove it, there's this delete of the root queue disk. So for network chaos, the same, more or less the same idea. We have a specific network chaos here where we can only set how much packets we want to lose. And again, we have a selector and everything. So I will do a quick demo of network loss, and then I have to be really fast because I'm running out of time. I deploy a deployment called Godot, which is a busybox waiting infinitely. I use that because I want to ping outside of the pod. So I actually lose network packets for egress. And when we take a look, when it runs, let's just quickly do a ping. Let's do it 10 times, and let's try to ping the Google DNS. So at the moment, everything works fine. Nice. We don't really see any packet losses. Let's apply our network chaos. It will be 50% network chaos for this Godot Godot pod. And let's do that again and see how many packets we actually lose. Of course, it's a chance to lose 50% of packets, so it doesn't mean that we will be, oh, wow, 50% loss. But it doesn't really need to be 50%. It will be around 50%. The longer we would run it, the more accurate we would be, of course. So let's take a look at the backend, the daemon, quickly. This is the interface that I defined as a protobuf definition for the daemon that's deployed. And when we go through the daemon code, here's the first server implementation of this kill container request. What we do is we connect to the containerd socket and use the containerd gRPC interface. There's also an official crate to interact with containerd. But here we do just a kill request with the containerd that we get from the request, and we send it to the containerd socket. And that's more or less it for deleting or killing a container, a random one. For traffic control, it's a bit more involved. First, we need to find out the PIT or a PIT of the container or some PIT of the pod. And for that, we use this file system that is provided by containerd to find the init PIT file, which then contains the initial process ID. And what we then do, and this is the magic more or less, we do just an NS-enter. We enter the network namespace of this PIT, and then we do just a TC and queue disk with a replace instead of an add, but we do a netdem and that's more or less it. And that's how it's set. The network chaos has a finalizer, so when the network chaos gets deleted, we first, of course, want to clear the queuing discipline. So we just do a flush, which does more or less the same, but deletes the queued discipline. So that's it. You can find the code in the carries repository in my GitHub user, and this is an email. You can contact me if you have questions. So yeah, thank you, and enjoy KubeCon next week.
Thank you, Yannick. Unfortunately, we don't have time for questions. So 5 minutes break, and we're going to kick off the next one. Thank you. if you want to chat. So yeah, take your coffee and move there. The stage is yours.
Thank you so much. Well, a very warm welcome to all of you to the KubeCon Rejekts. We are delighted to be talking to you today. My name is Louise, and this is Ben. We're both from Canonical. We're software engineers, and we work on a Kubernetes distribution, or actually multiple ones. Today, we're talking about hardening Kubernetes, which has been one of our recent projects, and our journey to FIPS compliance. We'll start with going through the compliance landscape. Then we'll move on to the challenges that we faced, getting our Kubernetes distribution into compliance with FIPS. And we'll close after our challenges, obviously with a happy ending. And we'll take it from there. This is the compliance landscape. And so maybe a few of you in the room were like me a couple of months ago, and we're like, what the hell is FIPS? So my thought immediately went to, okay, FIPS is like the feline infectious peritonitis, right? Obviously. We just adopted a cat and that's what she had. So we're like, yeah, it's probably something like that. But actually it stands for Federal Information Processing Standards. So it's not a disease, might feel like that a bit sometimes. But actually, yeah, it's a security standard brought to you by the US government. So this standard is published by the NIST Institute, which stands for National Institute of Standards and Technology. The related framework is FedRAMP. It standardizes cloud security and assessment. And then what does it actually define? It has a bunch of standards, and those are about the approved cryptographic requirements. Lastly, all right. The most quoted one of these is the FIPS 140-3 at the bottom here, which goes into the crypto module validation. Now, why do we actually need this FIPS stuff? So it turns out regulated industries like the government or any parties associating with the government, in order for them to do business with us or you have to comply in this environment and uphold these standards. It also offers trust. You know that the software you are using is following these standards laid out by the government, and you have that standardization. So it's not like I was on my train here and I YOLO'd crypto and that's going to be in the next Kubernetes distribution. So you have that assurance that the crypto that is getting used in the software is actually following this regulation. Now, how does one get FIPS certified? Okay, let's say I was really motivated and I wrote this crypto library, the HashiHound, on my way to Amsterdam. So I'm done developing my crypto module. Now it's going in for independent lab testing. So this is not just something that I can do myself. It has to go into an actual lab, and there's a good process around making sure and validating the algorithms used behind this module. And once those tests are done, it goes to NIST and you submit it for validation. So then you wait another time and see that all the lab testing and everything goes right. And once it's got submitted and validated and everything is well, you get to put your lovely module onto the list of FIPS validated cryptos. So what are some of the cryptos that are already validated? So here's a list. Maybe you recognize some of these. Our little HashiHound is obviously our fictional crypto, also made it. But yeah, so you might recognize some of these, but there is also plenty that are not validated yet, like MD5, for example. All right, so how does FIPS shape cloud native architecture? So some of these FIPS softwares, you have to obviously use the libraries. When you're writing your application, you can't just use anything out there. They have to uphold those standards. And then each microservice that you have running also needs to be validated to comply. And every update you do, every little change that you make has to obviously then be validated again. And now we'll see what all of this means for our Kubernetes distribution. So we went through the process of ensuring that our product is FIPS validated. This is our Kubernetes distribution in a nutshell. Obviously, we use vanilla Kubernetes at the core, but on its own, that's not your full product. So you need something for your pods to talk to each other, like a network. So we use Cilium. You need a container runtime. We ship with Containerd, for example, and then a storage solution and a couple of other features and add-ons as well. All of this bundled together gives you a self-working cluster that you can then deploy your own applications on top of. So we provide the base with something that works, and then you can deploy your applications on top of it. So now we were at the start of this journey, and we were thinking, okay, how are we gonna do this? We use a lot of features, and we need to make sure that everything is FIPS compliant that we're putting into our Kubernetes distribution. So how does this process work? So we have a Kubernetes release every 4 months. We take that, we put our features on top of that, and we'll have to audit every single component that we're putting into our distribution. We'd have to identify everything that we are using, whether it's FIPS compliant or not. Then one solution could maybe be we patch out the source code and fork it and replace all the non-compliant algorithms. Maybe this is very unmaintainable. If we can do it, we'd have to rebuild the distribution, test and validate it. And every single time we change a component or update something, we would have to reevaluate everything. So the cycle certainly seemed like a first idea, but it wasn't going to be a maintainable solution. It would have required way too much time and effort to go through this process each single time for a release or just for maintenance. So that leads us to
all right, that leads us to a bit more technical details now in terms of how we're going to achieve FIPS compliance on a Go level, basically. As Luis said, it's not really scalable to kind of look at every source code and try to patch out FIPS compliance. We still have to patch it to make it FIPS compliant. So we need to find another way. And of course, FIPS is kind of a big deal for most big corporations. So we're not the first ones actually trying to solve this issue. To understand the way we're going to solve this problem, we first need to look into. I mainly focus on Go for this discussion. For that, we first need to understand how does actually a Go binary look at its core. Yeah, sorry, forgot that slide. Basically, Go by default is not the crypto implementation of Go is not FIPS compliant yet. Starting from 1.24, they actually make efforts to make it FIPS compliant, and it's currently going through lab testing and all this bureaucracy that Luis was defining. So that's why, in theory, Go will be FIPS compliant once they are validated. But right now, we cannot use native Go and the native crypto implementations because it's still in the process. So we needed to find some alternative for now. Okay, back to how does a Go binary basically look like. On a high level, you have your Go logic, of course, and you have the Go runtime of the scheduler and everything. And then Go code can, of course, pull in any kind of crypto implementation or any standard library from available, and then it will be pulled in statically linked into your binary. So you get one binary that is statically linked, and every component that it needs is in there. And it will not reach out to any kind of host system or so on. For FIPS now, the approach is to actually reach out to the host system to get a FIPS certified implementation of your algorithms. So how does this look like? If you compile your Go with a special toolchain from Microsoft, it basically will forward all of your calls to crypto to the underlying host. To do this, there are two things that need to happen. On the one hand, of course, you need to enable CGO to link against OpenSSL, and you need to build the whole thing, your whole binary dynamically to be able to do this kind of linking. So how does it look like? Basically, whenever your Go code will do any kind of crypto, will call any of your crypto algorithms in standard Go crypto implementation, it will not use the actual Go crypto implementation, but instead it will reach out to the underlying host. And then you need to ensure that your host system uses a certified implementation. For example, OpenSSL if you configure it correctly. Okay, so what is the problem here? Well, of course, the whole stack needs to be FIPS compliant. That means also your operating system and kernel need to be FIPS compliant. There are a set of different ways of doing that. Of course, we're going to tell you the Ubuntu way, which is we use Ubuntu Pro. Ubuntu Pro has like a FIPS implementation to make a FIPS feature to make the FIPS kernel available for you. We're going to later see that in a short demo. Okay, so that basically sounds rather simple. We compile all of our Go binaries, the features that Luis described, the core Kubernetes binaries. We recompile them with the Go toolchain that forwards all of the crypto to the underlying host. Sounds relatively simple, but of course there's a lot of problems with that in detail. One of the problems I want to go deeper a bit more is the dynamic linking that I explained it earlier. It's a mess. Basically, to show you one of those specific examples that issues that you run into is with Cilium. Cilium does a very interesting thing. It basically runs a set of binaries on the host namespace, on the host system. So basically, if you start a container, it will also try to it will also copy binaries on the host. For example, symount sysctl fix, for example, and they will do several configurations for your on your host, basically. That works okay if you statically link your binaries because you're not dependent on anything on the host. But if you now start to dynamically link and dynamically build your binaries, well, then you generate a dependency on the host. So that's one of the problems we ran into. We dynamically built the Cilium binaries. We started to, if you then start to run them, you get the dependency on the OpenSSL of your specific OCI container, and that works well if you run on the same Ubuntu version, for example, for that is the base for your Cilium OCI container. But if this is not the case, then you run into the dependency issue because several problems. One of them is, for example, your OpenSSL path might change, and then you point to the wrong OpenSSL module, and it will just break. So there's a couple of issues with that, and what we needed to do for that is basically to solve it. We generated a wrapper binary. This wrapper binary embeds all of those the binaries themselves that Cilium provides, each of them. And then it will, when it is copied to the host, it will create those binaries themselves and configure the runtime environments for those specific binaries on the host. With that, you can kind of point to the right libraries, even if you're not running inside your container. Sounds a bit messy. It maybe is. It probably is. But yeah. At the end, you get a kind of FIPS compliant binary with that. Okay, as you see, it's a bit messy, so you need to have a lot of testing and validation that this stuff actually works. So to do this, it's rather complicated or actually not really possible to, or it is possible to perform automatic verification of FIPS. Why is this problematic? Because there's also manual review involved, right? This approach that I showed, this only works if you use the Go crypto. If some user for whatever reason decided to implement their own MD5 algorithms, they can do this, but this is not certified. And then you need to, what you need to do, you need to go ahead, need to look at the code, say, oh, okay, this is not FIPS certified, and then you need to patch that out or try to find some other ways. So this approach only works with the standard Go and not with some custom algorithms. Okay, so to do this, we, as said, manually we cannot. We need to have manual reviews, and what we can test is actually that we test with the correct, that we run with the correct Go toolchain, the one that we just saw from Microsoft, and we can do that, and then we can test for the inverse case. We can test that the binaries fail if you try to do something not FIPS compliant, and this is exactly what we're doing. We're doing this in 3 steps. So first is, of course, the rocks, the OCI container, basically. We test unit test that if we set a specific environment variable, we expect the binaries to crash. We will later see this in the demo. And then the next step is if we pull those features, if we pull those rocks in our Kubernetes distribution, what we do is we test that those rocks that we pull in, or this OCI containers that we pull in, that they actually are with the same toolchain, so that there's not something, there's in different repositories. So it could happen that, for example, for whatever reason, there would be a wrong toolchain or something. So that's why we also verify this on the canonical Kubernetes repository. And the final step is basically the end-to-end verification, where we test that on actual FIPS hosts, we actually test all of the integration testing of our distribution. And if there's also running on FIPS container and FIPS versions with different operating system versions, then we have like kind of a baseline verification. We have a verification that these things also, that our distribution also works on FIPS. Okay, cool. Let's see a quick demo on that. So let's see. How can I share this? Share something else. Can I not just share the screen? Can you share the entire screen? Yes, but this one. Oh, there we go. Thank you. Okay, so we have 2 VMs here, Ubuntu VMs. The first one is just a normal Noble version, and the other one is a FIPS host. We can check this if we look at the proc file system. Oh, go on. And here we see we don't have a crypto module, and we can see crypto enabled. And here you can see basically that the kernel tells us, hey, this is a FIPS certified kernel, which we don't have in the upper one. Okay, and now I already went into let's clear this one. I already went in the path of the K8s distribution, and we have a set of binaries here. And what we see now, those are all the binaries that we compiled with this special Go toolchain. And we can now, for example, let's start the Kube API server. And we see this works because it will automatically detect that this is not a FIPS machine, so it will not try to run any FIPS stuff. When we now try to force this guy to run in FIPS mode, it will basically tell us, hey, this is not a FIPS machine, this is not a FIPS compliant environment that you're running your binaries into, and it will just panic. And now let's try the same thing on a FIPS machine. We can see that here it will run. Of course, it will not run because I need to configure stuff for KubeCon server, but it will not crash. It will not panic. Okay, I guess that's so much for it. If there's any questions, so happy to answer them. Oh.
Yeah, so when Go gets FIPS compliant, do you foresee any problem changing over to that with this solution that you did? Or is it just like, just replace it really easy?
Well, I don't see as immediate problem with replacing it, but of course you may need to define an upgrade path, but this, yeah, I would say it should be rather smooth because to some extent it's an implementation detail, I would say, right? And it will probably be less troublesome because you can get rid of the dynamic linking part and everything. So, which basically are the most issues that we run into. So, would probably be more smooth. So we're really looking forward to this kind of certification to not need to do this dance. It was not.
One question on FIPS and your approach. Obviously, you're going all the way through to certified, but was there any talk about differences in approaches for FIPS compliant versus FIPS certified?
Yes, that's actually a good point. Even if we give the users a certified or a FIPS compliant Kubernetes cluster, it's still not FIPS certified because you can only certify appliances. That means the customers take this thing, they do their own workloads, they deploy their own workloads on top, and then they go ahead, and if they really want to have a FIPS certified cluster, then they need to, or certified workloads, then they would need to go to all this bureaucracy process themselves. So this is not something that we as a workload, as a distribution provider can do.
And a quick follow-up. Did you have any special approach or anything on like your SBOM, like the bill of materials side and all that? Did you have to do anything to basically show evidence that we are FIPS compliant in these builds, or does that just come through with typical SBOM?
I mean, we generate, of course, the SBOM, and based on that.
Can you speak in the mic, please?
Oh, sorry. So, of course, we generate the SBOM for that thing, and there you see we provide a way to say, okay, this is built with this tool chain, and the tool chain would be within the SBOM because there's basically a special FIPS Go track for the Go snap there. So you would see that this is compiled with this particular tool chain. Does this answer your question? Yeah. Okay.
Anyone? I have one. Is that like a publicly available for a community, or it's a paid version of Ubuntu?
So this one is it's free, but Ubuntu Pro is not free. I mean, you have like 5 subscriptions for free, but then Ubuntu Pro is the kind of commercial offering. And this Ubuntu Pro, you would need to have this host kernel enabled machine. So you can just download canonical Kubernetes, can run it on the system, but if you don't have a FIPS certified system, FIPS compliant system, sorry, then it will not be FIPS compliant. So you really can just make use of it if you have Ubuntu Pro on your host machine, basically. And then there you enable the FIPS plugin or FIPS module, however you call it.
So the Kubernetes, it's for free, but the underlying OS is kind of okay.
So this particular FIPS module for the host, that's paid.
Thank you. I couldn't resist, but I need to ask, how hard is to maintain this approach?
It's absolutely simple. No, I mean,
okay,
there's
rephrasing. How much time it takes to maintain this approach?
Well, there's a reason that we look forward to the certification, of course, but it's okay. In the end, you need to treat it as a normal software feature to some extent, right? Of course, you need to have proper testing in place. There's some initial issues with bugs and everything, but once we stabilize this, I think we haven't run into any problems anymore. And the maintenance really boils down to automation, right? To some extent. Does this answer your question? Or? But yeah, it's an approach, I guess.
Right. Anyone else? Last call. Right. Thank you very much, guys. With that.
Good afternoon, guys. My name is Zicong Chen. Currently work at Huawei, and what is one of the Volcano maintainer. Today, my topic I want to share is your cluster isn't flat, a first-class API for real-world infrastructure topology. Some listeners might have listened to the Volcano project before, but while others may not. So let's quickly get to know Volcano. In 2017, KubeBatch open sourced it born as a batch scheduler for Kubernetes. And into 2019, Volcano open sourced, and the same maintainers from KubeBatch continue involved in the Volcano to build it as a comprehensive cloud-native batch system. And for now, Volcano has already become the CNCF incubating project, and we wish to look forward to become the CNCF graduation project in this year, and to expand the scope of Volcano to serve as a unified scheduling system. And here, let's get a quick overview of Volcano. Volcano originated from the batch scheduler, can do AI training, inference, big data GAN scheduling, and has been used by more and more companies in the production, and has reached for scheduling strategies, can integrate a variety of heterogeneous accelerators, can do queue management, and for now, Volcano is evolving from the only batch scheduler to a unified scheduling platform. So let's get back to today's topic. Why do we need network topology aware scheduling? Why do we say that your cluster isn't flat? The most current network architecture is use span leaf configuration. So consider the simplest scenario. If the two pods in a training job are performing a full machine training task, but the scheduler is unaware of the downside network topology. The worst case in the red line, we have to will require 5 hops. While one hop data exchange would be the best performance, most efficient. And for the inference scenario, PD separation has become the trend now. So because the profile and decoder pod has different resource requirement, while profile has more computer resource requirement, but the decoder needs a more memory bandwidth to consume the KV cache. So the transferring KV cache from the P to D requires high bandwidth. So minimize the number of hops can also improve the performance of the inference tasks. Therefore, the scheduler must be able to sense the network topology, to model the network topology, and place a group of pods in a same group in such an abstract network topology domain to improve the AI training to AI inference performances. Current data center network architecture is heterogeneous in the protocol and net topology diversity from the IB to Rocky NV switch. And current node label are flattened. It's semantics and it lack hierarchical semantics and health monitoring. So we need to build a network entity, a network topology entity to help scheduler know the downside topology. Most of the existing scheduler are already abstract the network topology to building by defining a sign of topology hierarchical labels through CRD first, and then labeling them in the corresponding node label. We're thinking that it's okay in the short term because currently there's a common practice in Kubernetes after all, there's no entity to represent a switch or network domain currently. Only had the node API. But it has a fatal flaw because labels are just static strings. There are stateless and flat. When we use a label like span equals switch one, the scheduler only knows that a group of nodes share the same string. It knows absolutely nothing with the switch itself. What is the total bandwidth of the switch one? It is currently congested. It's a pull down. Labels cannot answer these questions. So in the long run, we must have an entity to build such a network topology. We're thinking that no label currently make the topology too cumbersome because you can only flatten your topology to the downside node. It's difficult to visualize your topology. So Volcano has already built the Hypernode CRD in previous version and already used the Hypernode to do network topology aware scheduling. Hypernode can only customize the hierarchical relationship, also can expand the more field and cooperate with other resources to support more topology in the future. Hypernode can also monitor the health status of the network topology and to optimize scheduling according to the network congestion status. So for a classic span-layer architecture topology, Hypernode is built in this way. Just see from this picture, the green node can represent the switch or the network domain in the same performance. So the blue item is the actual nodes. We build Hypernode in this way. It has a leaf Hypernode and has a non-leaf Hypernode. So the Hypernode example here. To standardize, Hypernode can standardize the cluster topology by performance domains. So after the introduction of the Hypernode API, manually building the Hypernode is relatively complicated. So Volcano also provide a mechanism for automatic discovery for the Hypernode, which can integrate the other solution like the node labeling and can also automatically generate the Hypernode through some network discovery like the NVIDIA Fabric Manager. And we are also looking forward to integrate more other discovery further. In previous version, workloads could specify network topology requirement at the pod group level. Constrain a group of pods within a pod group to the same network topology domain. And Volcano also currently support this. For example, when a pod group contains multiple subgroups, but with different network requirements. So each subgroups needs to satisfy their each network constraints, enabling subgroup level GAN scheduling and a network topology aware scheduling. And Volcano has already integrated Hypernode level bin packing. If the Hypernode has already scheduled most of the pods in the same group, the remaining pods in the same group will continue to be scheduled into the same Hypernode. And currently, Volcano, the Hypernode only extend to support Hypernodes or nodes for the members, but it's not does not cover like the multi-rail architecture where GPUs with the same index are directly connected, or 3D towards like the TPU networks. But we wish to expand more fields or capabilities to collaborate with other resources like DRA to support more such network schemas, like DRA to handle the microscopic alignment, but the Hypernode can do the macroscopic network boundaries. And Volcano has already supported automatic discover. So already integrate the NVIDIA Unified Fabric Manager to support IB network auto discovery and the label-based network Hypernode Discover, which is most common solution for other schedulers. But with Volcano, we also look forward to integrate more network auto discovery solutions like the Rocky NVIDIA Topograph, which is the open source providers, and Cloud and Fabric managers. And we wish also to promote the Hypernode as a Kubernetes first-class citizen. As I mentioned before, no label can are flattened and can expand and can't explain cumbersome semantics. But for Hypernode, Hypernode is stable and can do dynamic scheduling. It has a status field, and we can continually inject real-time telemetry data into the status, like the packet loss rates or link health into the Hypernode status. So the scheduler can finally make decisions through the status field. And also, Hypernodes can easily to expand the multi-to-multi relationship. And it can extend more fields and collaborate other resources to expand more architecture, not just the span leaf architecture. So we wish to promote the Hypernode as the Kubernetes first-class citizen because Kubernetes only had the Node API currently, but the AI training and the AI inference are become more popular today. So we wish to promote it. Firstly, we want to do extract Hypernode to decouple the Hypernode controller as an independent vendor-neutral API standard. And second, we want to call for the co-creation of the Hypernode initiative, like through the via CNCF TLC to join, define, and manage Hypernode standards. So here's all my contents currently, and here the Volcano QR codes for the GitHub and Slack channel, and we wish to expand more community users today. So thank you. Yeah. Yeah. Any question? Because my English may not so fluently. I'm not sure my translator may be correct. But
You're doing great.
I can answer.
Anyone questions? All right.
Sorry. Hey, sorry.
No.
I'm really excited about this. I think it's great. One question though, and I know you mentioned like network aware topology and things there. We've got a challenge related to scheduling. It's like smart scheduling of workloads in situations where we are almost like dual or triple stack with guest clusters on KubeVirt, right? Nodes on bare metal Kubernetes, like that kind of triple stack. And you had mentioned briefly like NUMA aware topology and some of the challenges there. Wondering if Hypernode helps address some of the scheduling challenges there. And then also, can we be topology aware, but not necessarily include every node in that topology as a schedulable node, if that makes sense?
I'm not sure your question, but yeah, we can extract some nodes you want to you don't want to schedule in that hypernode. Yeah, hypernode can do topology scheduling to increase training AI training and AI inference performance. I'm not sure I have already answered your questions.
It's all good. I think it's going to answer my question, but I'll follow up with you afterwards.
There was someone else. No? In that case, thank you very much. The next one will be at 5:05, I think. goodness. Welcome everyone. That is our last session for this room for tonight, for this evening. We have Simon and Lovro. I was gonna screw up that. They're gonna talk about KCP and Crossplane. So take it away. I'm sorry guys, for the folks in the cafeteria, can you move to the hallway?
Or even better, move in here, maybe. All right, with that, getting started, thank you for the introduction. Today, I will inform you, we are not the last talk that's keeping you away from beer. There's still lightning talks, but it's going to be exciting. So let's talk about it a little bit. Hi, I'm Simon. I'm a software engineer at Kubernetes, and I work full-time on KCP. And that last sentence triggers this slide, basically, which I'm gladly to inform you that part of my work is funded by the European Union through a project partnership with SAP. So if you're a European citizen and you pay your taxes, thank you. You have helped create what we're about to see. Today, I'm not alone. I'm joined by Lovro.
Hi, everybody. My name is Lovro. I'm an engineer at Abound. I contribute to Crossplane, maybe not as much as I would like. But yeah, I'll talk about Crossplane a bit today. And I'm unfortunately not funded by EU, but if somebody wants to fund me, I'll give you my OnlyFans.
So let's get into it. So who of you guys already knows what KCP is? Quick show of hands. Perfect. We can basically skip the first part of this presentation. No, I'm kidding. Let's get into it. So we need to talk a little bit about platform engineering in general. And I don't want to bore you now with a 10 bullet point slide, but for me, two things are very important. It's that your platform should be automated and it should be self-service driven, meaning a consumer decides when they want to consume a service and then an automation triggers. Because if we don't have these two things, we're quickly building a ticketing system, and heck knows we have enough of those already. We don't need another one. So with that out of the way, let's consider a really simple example. So we're going to have some provider teams, certificates, databases, for example, and then we're going to have some consumer teams. These could be like application teams that want to have a certificate or a database. And then in between, this pink box is our internal developer platform that handles all the magic in between. And the typical flow could be, we look for what are services that are available. We decide, oh, databases are really cool. We order one. The database team gets notified about the order, and then there is some sort of fulfillment, for example, provisioning the database and sending the consumer some credentials so they can actually use it. All pretty straightforward so far. However, building this pink box is nothing simple. Yeah? And one of the big things that comes up often is we need an API layer for this because we have several components that want to talk to each other, that want to interact with each other, and they need to have a shared API. And it starts always with this question, hey, what if we just use Kubernetes as an API layer? And Kubernetes we know from container orchestration, but it also has a rather sophisticated API. And when I say sophisticated, what I mean essentially for our use case is we can use groups to track the owner of an API. We can use versions to track the life cycle of an API. And then using this combination of namespace, resource types, and names, we can uniquely identify objects in the API itself. The second cool part is there is an API in Kubernetes to register new APIs. It's called custom resource definitions. And essentially, this is something that a provider could really easily use to just make their API available to consumers. Nice, 3 minutes in, we're done with the talk. You know, we're just gonna get one big Kubernetes cluster, everyone's happy, we're done. Yeah, not really. So one of the big things is Kubernetes was never designed as an API sharing type of platform. And as such, it hasn't had some of these considerations. One of the major things is these CRDs, or more specifically, the resulting APIs, they're just shared globally. I'm not talking about the objects, but I'm talking about the API itself, which might not be desirable in a shared responsibility model where a provider only wants to advertise certain APIs to certain consumers and don't want to make them available. Then you say, okay, Simon, no problem. I just have really a lot of money lying around or a lot of computing capacity. I'm just going to give everyone a cluster so that we have this isolation. And even if that's the case, one thing that's really going to bug you is it's still going to take a long time to ramp one up. Imagine every time a new consumer or provider comes in and it takes 20 minutes or 10 minutes for you to ramp up a cluster. Still not fun. So then this idea comes up if, What if we just make these lighter? So instead of taking the full Kubernetes, we're going to rip out some of the things we don't need, like who needs container orchestration? We just want to share APIs. And we create these lightweight control planes that are left over, and every control plane essentially has its own store of data. And everyone who has done this knows that building a syncer between all of these is a pain to do, because imagine every time a new consumer or provider comes in, you have another n in your complicated n times n plus 1 calculation. So, and this brings us to this idea, what if these control planes, instead of everyone has their own data store, they could just share the data store? Sounds pretty logical. Let's look into this. And this kind of, I think, is the idea that birthed KCP a little bit. So KCP is a cloud native sandbox project. We're trying really hard to become incubating. So fingers crossed that we'll get it. And of course, like any other project, we have a cool one-liner to perfectly describe what we do, but that doesn't help you at all if you're starting out. Yeah, it contains multi-tenant, control plane, Kubernetes-style APIs. Sounds really cool. But I thought maybe the best way to explain it to you is we're starting with a little example. In this example, you're this person, the stick figure on the left, and then on the right is KCP that we want to interact with. And the best way to start is KCP basically is a Kubernetes API server. And as such, it connects to a data store. That's 99% of the time just etcd. But for being perfectly honest, I'm going to have to write etcd compliant on these slides. And as such, because it's a Kubernetes API server, you can interact with it using kubectl, like you would with any other Kubernetes API server. You could run kubectl get namespaces, and it would return something for you. Now, the big part that we have is this multi-tenancy that we saw on the definition before. And what it basically boils down to is, in KCP, we can create tenants like we could create other objects. So there's an object type that we can create, like with kubectl, and then some magic happens behind the scenes. So we'll talk more about the magic in a minute, and it's going to provision a tenant for us inside of KCP and ourselves, and then it returns a kube config that's valid for only for that tenant. Same goes, another team could go ahead and they could have their own tenant as well, which is exactly what we want in these multi-tenant type of systems. Now, the important part, of course, is if we were to use this kube config that's only valid for this blue tenant, we, of course, would also only get objects back from this tenant, which is intended. We don't want team A to see what team B is doing. Now, I know this all sounds very abstract, and I promise to you by the end of the talk, you will get a little bit of a deeper understanding. But before we can get into this, there's two more things to mention. The first thing that you see on this slide is that I nowhere drew a Kubernetes cluster. Yes, I drew a logo for Kubernetes API server, but there is no Kubernetes cluster. And this, I think, is very important. KCP is independent of Kubernetes. Yes, it behaves like a standalone Kube API server, but it doesn't need Kubernetes at all. It's completely independent. This, of course, comes with an implication. It also means that you cannot use KCP to schedule pods. You cannot do kubectl create pod that doesn't work, that doesn't exist in there. But this is intended because we want to build a platform for sharing APIs. We don't want to build another container scheduling solution. We'll get into how these two work together to actually get the wanted effect a little bit later. The second part that you see is, if you look closely, you can see I only used this API server logo once on KCP itself, and that's really important. KCP is not some sort of proxy that spins up new Kube API server processes and then forwards traffic to them. These API servers that we see here, they exist solely within the memory of KCP or later in the data store. And to give you some insights, so one of these API servers is around 3 megabytes of memory footprint when there's no content in it. And as such, and I think because this is very confusing to reuse the term API server twice here, we actually use the term workspaces inside of KCP. So the workspace is the name for the multi-tenancy. Now, everyone looks very skeptical, and you're absolutely right. Now, let's look a little bit into how does this actually work behind the scenes. And the way it works is we organize these workspaces in a tree, much like you would organize files on a file system. And then we use the unique path of a workspace in a tree in the server URL of a kube config to be able to know which workspace you want to talk to. Of course, each workspace has its own role-based access control. So you cannot just because you know the workspace URL of team B doesn't mean you have access to it. You still need valid credentials. All right, let's do a bit of a practical example. We have a big demo at the end, so I just have it on slides, and you just have to trust me that it's like it says on the slides. But here, let's get started. So KCP, it's a binary. You can just start it. It will connect to an etcd. And then it also will spit out an admin kubeconfig for you. And like you would use with Kubernetes, with kubectl, you can just set your kubeconfig to the admin kubeconfig, and then you can start creating objects. And namespaces or config maps and secrets are objects that also exist in KCP. And then the other part is you can, of course, create workspaces as well, like you would create the other objects. And then there's a special thing, there's a kubectl workspace plugin that allows you to switch workspaces. But switch is a really big word. What it does is it changes the server URL to now match this new path so that KCP knows you want to be talking with that workspace. And most importantly, these workspaces are isolated. So we've created the namespace foo in the root workspace. And of course, it doesn't exist in the Team A workspace because they are different tenants. With this, you say, OK, Simon, that's great. I understand everyone gets their tenant and it's isolated. But we wanted to create a platform for sharing APIs. And now everything's isolated. So how can we do that? And for this, there is a feature called API export and API binding, which are two native objects to KCP. And the idea is in an export, you can make the API available to other tenants. And then in a binding, you say, hey, this is an API I want to import. I want to bind into my workspace, thus creating the necessary APIs in my workspace. So let's look into this into practice. And it is very straightforward. An API export is just a list of resource schemas. A resource schema looks like a CRD. So it's just a list of APIs I want to export. And then in my binding, what I'm going to do is I'm just going to reference that export, and I'm going to reference it using that path that we saw before, that unique path that identifies the workspace of the provider where the API export lives. OK, then you say, yeah, Simon, I understand this. So they have the API bound, but someone has to do the actual work, right? There's some sort of controller involved that I wrote that does the provisioning of the database, that creates the secret, and so on. And we've already learned this cannot live inside KCP because KCP doesn't do container scheduling. So it lives somewhere outside. How the hell does this pod now know that someone has created a database in some isolated tenant on the other end of the world inside KCP? And for this, and I promise this is the last cool KCP feature you need to learn for today, and then we're all settled for the demo. There is a feature called the API Export Virtual Workspace. And I could probably give a whole talk just on this feature. But for now, you can imagine the following. There is a built-in feature into KCP that allows you to aggregate all objects of an API export type that you own, and you can generate a kubeconfig from it that you can feed into your controller. So essentially, database controller will know about all database objects that get created somewhere in KCP. And the cool thing is this is fully dynamic. So if Team B decides our databases are really cool and they create an API binding, you will automatically get events for those as well. All of this comes with a teeny tiny asterisk that will become relevant for our demo in a minute. So this works really, really well if your controller is built on multi-cluster runtime, which is a pretty much drop-in replacement for controller runtime. But often you don't have this in your control. And we'll also tackle in a demo a little bit how you can handle this if you have a controller built on controller runtime and you want to make it work in this multi-tenant world. For now, I know this is all a bit magical in the beginning when it's the first time someone telling you this, and it's almost too good to be true. You will hear this constantly as a theme, as a little bit of this talk. You have to trust me on some of these things, but I'm happy to discuss details with you also over a beer. With this, we're handing over to Lovro.
Okay, so you see KCP is really cool, can do a lot of magic stuff, but how to actually use it? So I'll just talk a bit about Crossplane and give you just a little bit of intro. I won't go too deep because we don't have so much time, and hopefully more people know about Crossplane than KCP for now. Okay, so quickly, Crossplane is the cloud native control plane, right? What does that mean? Basically, it means that you can provision, manage, represent all of your resources, external or internal in the cluster, through resources in Kubernetes. Crossplane has some superpowers. One of those is that you can compose resources into higher level abstractions. So you can gather a lot of the smaller resources and make an abstraction that you can give to your developers. We all know that Kubernetes is a great control plane for containers, but Crossplane lets you expand that over everything else. So how to do it? So another superpower that Crossplane has is the provider ecosystem. So there's a huge marketplace with a lot of providers that allow us to talk with, for example, AWS, GCP or whatever. So for example, if you have provider AWS, it knows how to represent AWS resources and how to talk with AWS when you create those resources in your cluster. And then you can compose those into, for example, a cluster abstraction where you put in all those smaller resources like the node pool network or subnetwork, and you can give your developers just a limited config for that because you don't want all the configuration details to be exposed. For example, you just give them like an enum, small, big, and that's it. And in the background, you can control based on those inputs how big is your node pool, for example. So basically, you can give your developers like a golden path into provisioning infrastructure, and you get rid of tickets. Okay, let's get into the YAML. So how to define those high-level resources? We do the thing is called composite resource definition. Sounds very similar to CRDs, right? And basically, they look the same. You define your kind, your name, and you define the schema. And you can put in the schema whatever you want to be in your input parameters. And then to tell Crossplane what to do with it, composites, we create compositions, which based on the composite that's coming in, put this composite through a pipeline of functions, which all do something different with the composite. For example, in this, there is a generate resources. You can imagine generates a lot of YAML resources. Sends it to some filter, and in the end, you get a list of resources, YAML resources that get applied on the cluster. So a bit more about that. There's like a little graphic that explains it. So you create the composite, Crossplane takes it, runs it through the functions, gets a list of resources that get provisioned in your cluster at first, but then the providers pick them up and provision them, for example, somewhere in the cloud. Okay, basically, that's all I wanted to say about Crossplane. I think this is enough.
All right, let's dive straight into the demo. So on a high level, what do we want to achieve? So we have our member of Team A, our consumer. Then our provider, of course, has its own cluster. This is also where they could have their databases actually running. And then what we want to do is essentially we want to go ahead and the member of Team A, they create a database. We in our cluster know that the database has been created. We do all the provisioning. We create credentials and we're going to send them back so the user can enjoy their new database. Now, if you have been paying attention to this talk, you notice that I said everything works really, really, really nice if you have multi-cluster runtime. But what if you don't? Like if you're running an already existing controller. And for this, what we have built is a tool called KCP API Sync Agent. And what it does for you is it does this aggregation for you. It filters out all the objects, the database objects, and syncs them with a globally unique name to your target cluster. And that part is really important because on the left side, we have a truly multi-tenant system. Team A and Team B can both create a database called database1 in the default namespace. But on the right side, we need to be able to distinguish between them because they're two different databases. All right, let's put all the pieces together. So what we basically want is we have the cross-plane provider SQL, you can see on the right, and then on the left, we have a custom API called databases.mycorp. This is done on purpose that we have two different APIs because we want an API that we want to expose to our consumers, which contains only the fields we want them to be able to access. And then we kind of have a working API that's given to us because well, we are not the maintainer of the cross-plane SQL provider. We're just merely using it. And we might don't want to allow it to set all fields. So then they create a database. The sync agent, as told before, syncs them over. And then interestingly enough, the database microp, it's a cross-plane composition, which is what Lovro just mentioned. And that basically splits into the databases, users, and it creates an empty placeholder credential secret. And then our controller, it doesn't even know that it's behind the scenes is KCP doing things. It does what it always does. It operates within its cluster. It's happy. It's going to create a secret, and then it fills it with data, and then our sync agent is going to sync it back so that we actually, as Team A, can run kubectl get secret. Enough slides. Show me some real stuff. And that's what we're going to do now. So we're going to hop into the demo. And for this, Lovro and I are going to do a little bit of role play. So Lovro is the provider. You can see here in the bottom. And then, whoops, and then I'm the consumer. So I'm connected to my KCP workspace, and Lovro is connected to a kind cluster, which is supposed to symbolize the database cluster. Lovro, take it away. I would hold the mic for you if you want to.
Does this one work?
Oh. Okay.
Okay, let me try like this. Actually, this is it. This is easier. Okay, so I'm on the kind provider. On the provider cluster, I run crossplane on my cluster. You see it's installed. It has a function called Go templating, which does Go templating, and has a provider SQL, which knows how to create SQL databases. We can see that the provider has created some of the resources that it knows how to manage, like databases, users, and so on. Okay, so let's check our composite. So we created a composite, which is pretty simple. It's called MySQL database, and the only thing in its spec it has is the name, and it has some status with properties that we want to sync back at one point. Okay, and now I want to publish this resource to any of my consumers. I want to say, okay, I have the composition first. So what to do with the composite? So let me just show you the Go templating thing that we are doing. It's a composite working on the MySQL database using function Go templating. Everything is here inline to make it easier. And basically just creates a database that the provider knows how to handle. This part is important. It creates a secret that we want to expose and send back to our consumers. So just keep in mind of this label, which has sync agent KCP selector. This is how the sync agent will know later to take this secret and sync it back to the consumer. We fill it with user connection details, so it has all the data that they need to connect. And we create some secret with the user password. We create the user, and we in the end put the status for ready back into the composite. Okay, and we want to publish it. And let me just show you how to do it. So there is a sync agent publish resource thing. And what it does is we can select the MySQL database. We say, okay, in this version of this group, we want to publish it. And some things that are important here is the naming, because we don't want to reuse the same name that is in the user workspaces, because we can get conflicts. So basically, we just take the cluster name, which is the workspace name of the consumer, and just hash the name. Another thing is the related resources. So we're coming back to the secret I was mentioning. We can mention that, okay, there is a secret that we want to sync back, and it's just through the match labels. We can say, okay, if something matches this selector, sync it back. Okay, and let's apply it, and now we are published. And take it back, Simon.
Yep. So you have to hold the microphone. So we're gonna go now over onto the consumer side, and for consumers, the first thing that's really important to us is we need to actually bind the API so that we can use this API, and we do this via an API binding, which was also shown on the slides. And then there's one special thing is we also need to give the sync agent access to create the secret actually in our target namespace later on. And that's what we do here. Because it's a demo and we need to be quick, we just used star as a verb. You can think of it that you can make it a bit more secure for your production environment, please. With this, so we're going to apply the API binding, and now we have to be patient for 2 seconds, and then we should see, yeah, we can see now the databases API is available for us, which brings us, of course, to the next logical step, which is we actually want to create a database. In this case, we just expose a singular field. But like we said, you compose this API so you can decide which fields you want to show to the consumer as the provider. So let's go ahead. Oops, hello, where was I? Oops. So that's going to apply it. And then let's check. Our secret is already there. So it all went really, really quick. So we're going to head over to Lovro real quick on the provider side to see what happened behind the scenes.
Okay, so a consumer has created something. Let's check what it is. Oh, wait, I'm using the ring one. 13. Okay, so we see that we have a database created. The name is totally gibberish because we're hashing everything, but we don't mind because it's from a consumer. You can see that the secret was also created. So we have the secret for the database that we synced back. And do we have something else? I think it's it. And we can see that the managed resources were created from the provider, from this composition that we're talking about. So there's a database, there is a user, and we can see if the pod is created. So we can probably also see the MySQL pod is created. So Crossplane did this job. We provisioned the database for the user. The user only got the connection details to it, doesn't know anything about how it was created. And yeah, are you happy, consumer?
All right, with this, let's return real quick, promise you the last things. So yeah, get out your phones. QR codes are now flying in for you. So if you want to try this demo yourself, you can just run it on your computer locally, completely scan this code. 5, 4, 3, 2, 1. Okay. And yeah, today marks just the beginning of KubeCon. We have a ton of activities planned. I'm not going to go through this whole long list. One thing is there is a KCP project kiosk on Wednesday at 2 p.m. till 5 p.m. where you can meet a lot of the maintainers and contributors. So maybe that's like a highlight. But yeah, feel free to check out the blog post, which contains also links to all of these events.
Similarly for Crossplane, the QR code contains the blog post with all the links to the Crossplane related talks on KubeCon, and the Crossplane booth is open every day at the kiosk stuff. So see you there.
Okay, that's it. So both KCP and Crossplane are community projects. We hope you can engage into these. We would be done with our content. We have 2 more minutes for questions. We can stretch it a little. We will see. So questions. Okay, everyone wants beer.
So do I need to configure the kubeconfig for the Crossplane pods or something like that to make it work, or are the resources that are synced actually created in the cluster with the syncer?
They are created in the cluster with the syncer. So in Crossplane, in the Crossplane world, everything stays the same basically. Yeah.
Anyone else?
I think let's wait a second for the microphone and then so that people on the recording can also hear it.
I saw you had the asterisks. So is that for opening it up for everything instead of getting fine grain? Is that what that was?
No, so basically what the asterisk was for is if you're built on multi-cluster runtime, there's no need for you to have the syncer. Basically, your controller can natively watch the virtual workspace perfectly, and it knows in which workspace an object was created.
So the last thing is, so can you have all the workspaces be advertised without having them fine-grained?
What do you mean by advertised? Advertised to who?
Or like, how do you, like, you can look them up. You know how like you have RBAC on them. So like not to have like anyone can have access.
Yeah, so
free
so
open-
there's RBAC on each individual workspace, and also so the parent workspace, if you have RBAC permission to list workspaces, you can see the children of the parent, yes. But it's also, of course, you need access to the parent, which you would never give, right? You would give every team their own workspace, but you would not give anyone access to the parent. Okay.
Right, we are on time. Thank you very much, guys. With that, that was the last session in this room. We're going to go to the other one. There's another session about Helm charts version 3. And after that, lightning talks and closing. So thank you very much, everyone.
Stuff. Yeah, thanks. Good stuff. Thank you.